1, 2. Yep, worked. Thank you. One, two.
Test.
Sure. I'm okay. So, hello, thank you everyone to attend my presentation. My name is Flávio Solin. I work for Intel and I have been contributing with Zephyr for the last 6 years. I'm the current maintainer of the power management subsystem, and I'm also involved in other areas of the project. The presentation today, it's about power management, and my goal here is to provide a good overview of the features and the architectural framework that underpins Zephyr's power management capabilities. Additionally, I will also provide some guidelines to use and implement power management. So, why we care about power management, right? These are just a few reasons. First, to extend battery life, provide longer battery life for devices is very crucial for battery-powered IoT and wearable devices. Another good reason to care about power management is cost savings. Lower energy consumption translates directly to cost savings, and it makes products more competitive in the market. Another reason is environmental impact, since reducing power consumption contributes to lower carbon emissions. Regular compliance, it's another reason. Many regions have regulations to energy consumption for electronic devices, so we need to be aware of this. And even in user experience, less frequent charging, it's related with more user satisfaction. Definitely there are other reasons here, just a few. So these are the topics that I will cover today. I will start with the design and goals, and then I will cover power management implementation on Zephyr, and finish with how to enable and use it. Hopefully, we will have some room for questions as well in the end of the presentation. Okay, so design and objectives. First and more obvious, we want to reduce power consumption, right? We want to provide a way to consume as little energy as possible while we are still meeting functional requirements for a given use case and configuration. Secondly, this must be flexible. Different use cases and configurations have different power and functional requirements. Then it's mandatory to maintain responsiveness for the system. The system must be able to properly respond to events. Like be flexible, it must scale. It must scale from simple constrained devices to much more complex systems. And we aim to do this as much abstract as possible, providing a consistent interface for applications, as many other areas on the project. So what the subsystem does is provide mechanisms for a collaborative model where different parts of Zephyr, like device drivers, subsystems, and applications can work together to meet these objectives. So here are some key concepts that will help to navigate through Zephyr's power management. The first concept is kernel idling. Kernel idling, as we are going to see later, it's the code that is executed every time the system has nothing to do because all the threads are blocked waiting some condition. It's basically here where the system power management happens. Then we will go to the power management subsystem, see that the power management subsystem is divided in two major areas, system power management and device power management. System power management is done in the idle thread, as I mentioned, and it's responsible to save energy changing the associated power state. So power state can also be called idle state or sleep state, depending on the nomenclature, depending on the document that you see. On Zephyr, we mostly use power states for this. An important component of the system power management is the policy manager that we will see. The policy is responsible to make the decision about which power state should be used when the system gets idle, and based on the events and the possible conditions that were imposed to this policy. Like power constraints and latest constraints can be set to the policy that will change the decision that the policy can make. We are going to see later how the full policy works and how an application can change the behavior of this policy. The other major area that we'll see is device power management, that it's responsible to save energy, suspend devices. Device power management can also be static or dynamic. The static is when the devices are suspended together with the system. So when the system goes idle, we suspend the devices, and when it wakes up, we just resume them. And dynamic, on the other hand, it's more ad hoc. Devices can automatically, suspend and resume themselves. An example of device runtime is a UART. UART can get a reference from a GPIO driver when it's needed and release this when it's not needed anymore. If no one else is using this GPIO, the GPIO will be suspended. This dynamic device power management on Zephyr we call device runtime power management. So let's start with the system power management. So to understand the system power management, we have first to talk about a little bit about the scheduler and the idle thread. The scheduler is the main power management governance, since it knows when the next event will happen, and consequently can knows when to start doing power management. The Zephyr scheduler, it's a priority-based scheduler with optional round-robin time slicing. And this means that the scheduler will run first high-priority threads. So as you can see in this diagram, the scheduler will execute thread 1, then when thread 1 reaches a reschedule point that can be, for instance, caused by waiting on a semaphore, or yielding, or sleeping, this thread is marked as suspended or waiting. Then it will do the same for thread 2, thread 3, so on and so forth. Finally, when all these threads are suspended or waiting some condition, the scheduler will go and schedule a special thread that it's the idle thread. There is one idle thread per CPU, and it's created with the lowest priority. So this ensures that the idle thread is executed only when there is nothing else to do. One important thing to mention here is that Zephyr kernel is stickless capable, which means that the kernel is fully event driven, so there is no periodic clock interrupting the system. So here we have a high-level diagram of the idle thread. It's basically a continuous loop that every iteration locks IRQs to avoid being preempted during the power management sequence. Then if the target does not support power management, the idle thread just restore interruptions and put the CPU idle waiting for some event to happen. Now, when the system supports power management, then the idle thread will call the PM subsystem with the number, with the amount of the time to the next event that it's scheduled. The subsystem then may or may not suspend the CPU based on possible constraints, or if the time is enough to use one of these sleep states. If the CPU is not suspended, then it's exactly as if power management was disabled. Then the idle thread will just behave like without power management, just unlocking the IRQs and waiting for an event. And that it's all for the idle thread, basically. The key or trick part here is that at the end of the loop, interruptions has to be unlocked. So it's a little bit tricky because you start with the interruptions locked, and then you do power management, and at the end of this, you have to remember to restore interruptions. So from that perspective, system power management happens inside this function called PM system suspend, the highlighted box here. So this diagram on the left abstracts what the system power management basically does. In a nutshell, it checks with the policy manager which power state should be used based on the amount of the time to the next event. If the policy returns a state that it's different from active or runtime idle, the devices are suspended. I will talk about this later, but obviously this depends on device power management be enabled. And after this, the subsystem will call SOC API asking to transition to this state that the policy returned. When the CPU wakes up, the subsystem will, revert what was done. So we'll resume all the devices and finally, call this another SOC API that it's basically restore to give the system full operational again. And it's expected, when you return from this function, that the IRQs are unlocked. So power states. Power states for Zephyr, it's a way to describe, the multiple power mode savings supported by the hardware, and they were, inspired by the ACPI system states. These states, they have to be, declared in the device tree, so they can be accessible by other components in the system, like the policy manager. That we will use this information to, to select which state the CPU should be suspended. So we have 7 states counting the active state on Zephyr. The states go from active, where the system is fully, powered, to soft off, where that it's the deepest sleep state available, and that it's the one that consumes the minimal amount of power. Of course, as GPU is the state in this list, more is the energy that it's saved, but also it's bigger the time to transitioning and to leave from these states and to wake up the system. So platforms should, map their states to these ones. And in most cases, obviously, they don't have all these states, and that it's fine. They need to declare only the states that are supported by the hardware. There may be certain cases where, a target has 2 sleep states that would map to a particular Zephyr state, and for these circumstances, they can use a substate that would be, specific for this target. One important note here is Zephyr does not really impose which states the target has to implement, and we don't even, impose what has to be done in this state. We just provide, a general guideline and some expectations, but not really impose any behavior for these states. The policy will select which state that it's passed directly to, basically, the state that it's returned from the policy would be passed directly to the SOC. And the SOC, it's up to the SOC to do whatever it wants with this state. So on the left, I have a full representation of the power state in the device tree, right? Besides the state itself, we have other 2 properties that are a minimal residence, and that tell us the minimal time that the system should stay idle to be worthwhile energy-wise speaking. And the exit latency, that it's the amount of time required to the system exit this state and become active. These informations are used by the subsystem to program the timer in a way that the system does not miss any schedule event. So in the other side, you can see the definition of the power state in C, and in this declaration, you'll find description of which states it's equivalent, a description of the state and equivalence to ACPI when you are trying to do this map. Okay, so moving to the policy manager. The policy manager, as I have said, it's one function that it's called from the idle thread with the number of ticks to the next event, and it's responsible to return a sleep state or a power state. The default policy, it's based on residence time, and the logic is pretty simple. So it selects the deepest state available, that the minimum, so it selects the deepest state available, that the minimum residence is lesser than the time to the next event. The policy also accounts for, for the state and latency constraints that can be imposed by applications or subsystems. Applications can also, define their own policy. There is one symbol that they have to select, and then it's up to the application to create your own policy, define this function. There is one function here that it's this PM state force, that it's a way to bypass the decision of the policy. So if the application decides, to force the system to go to a specific state, can use this API. And in this case, the system power management will not even ask the policy what it's going to be the next state. The other, major area in power management on Zephyr is device power management. So first, device power management, it's enabled selecting the symbol PM device, and to support power management, drivers need to implement an interface that it's a callback, action callback that receives, an action that should be taken. This boils down to handle requests to suspend and resume the device. And in some cases, if the device belongs to a power domain, then you will also need to to handle turn on and turn off. I have mentioned it, but on Zephyr we have these two methods to do device power management. It's the static and dynamic. So static, it's also called system management power management. It's the one that when the system goes idle, we suspend and resume, and when the system wakes up, we resume these devices. Dynamic or runtime power management, that it's the nomenclature that it's more used, is the capability of suspend or resume devices automatically according with their usage, and that does not depend on the system power management. Does not depend on the system be idle to happen. One note, regarding system management, system managed power management, device power management, is that devices are suspended and resumed with their according with their dependencies. So it's we use the same dependencies that are used for device initialization. So we suspend device according with their initialization, then we, revert this when waken them. So coming back to the system power management diagram, after the policy returns the state that should be used, if it's anything, then active runtime, devices are sequentially suspended. The subsystem ignores some devices that depend on some conditions, like if the device is busy, or if the device is using runtime power management, or the device is used as a wake-up source. Then the system excludes this device from this list. Then after the SOC wakes, the devices are resumed in a reverse order that they were suspended. In a multi-core system, only the last CPU, only when the last CPU is going to sleep is that the devices are suspended, and as soon as the first CPU wakes, devices are resumed. Okay, so here's the part of Zephyr's code that checks the conditions for a device to suspend. So as you can see, if the device is not ready, or it's busy, or it's used as a wake up, or it's using runtime, then devices are not suspended. There is one option that you can even tune this, that it's PM need all devices idle, that if this option is enabled, if there is at least one device that it's idle, then any device is suspended. So now let's see device runtime power management. That it's the feature that allows device to directly power management even when the CPU is active. It's enabled when you select the symbol device runtime. There is no additional API that needs to be implemented. Suspend and resume, it can be done as synchronous and asynchronous. And there are many advantages of doing this, right? The system does not need to be idle to the device save energy, so you can save more energy when you do this. This also will speed up the system to the power management system, because the system does not need to suspend devices that are already using these and are already suspended, and the same applies to resume them. This method, it's a collaborative effort, so it really depends on device drivers doing the subsystems and application. So yeah, it's very important to emphasize this collaborative nature of this method, since none of these layers may have full knowledge of how to make the best decision about suspending and resuming a device. For example, a device may naively always suspend itself when it finishes an operation. This may be okay in some circumstances, but there may be some cases, where multiple operations are done, realized in a sequence, and this approach may end up, just consuming more energy than save. The same logic applies, for other layers, the subsystem may attempt to suspend the device without knowing if the application will need to use this. So the subsystem uses a reference count to check, when it needs to suspend or resume a device. And this way, each component can operate without worried about, each other, so that it's. As I have mentioned, there are synchronous and asynchronous ways to do the device runtime power management. Let's start with the simplest case, that it's when everything happens synchronously. In this example, we assume that the device is initially suspended. So as you can see, the idea is that when the application requests some operation from the device then calls PM runtime get, that will increase the reference count for this device, and calls the action callback to resume the device. Then the device do the operation that it's called, and when it finishes, the device will call the runtime put that will decrease the reference count, and finally, call the action to suspend the device. The asynchronous case, it's pretty similar. The main difference is that when the device finishes the operation, instead of synchronously suspend the device, it calls PM device runtime put async, and the PM subsystem will, instead of call the action callback, at that moment we will schedule the operation to the system work queue to be done later. We play some tricks here to avoid unnecessary work. So if there is a request canceling an operation that it's in the queue, we just do some adjustments in the reference, and we avoid changing the state of the device. Some additional notes here: device can enable and disable runtime power management at runtime, and there is only a synchronous API to suspend devices. This is a simplified version of how it works. In several cases, the application would be calling a subsystem, and the subsystem will be talking with the device for multiple calls. And in this case, the subsystem may be the one holding the reference also to avoid these unnecessary transitions. Okay, so finally, power domains. Power domain is an abstraction to group a set of the devices that are powered by a common source. On Zephyr, support for power domain is enabled with the PM device power domain option, and they are implemented just as regular devices. What basically makes a device a power domain is its relationship with other devices. This dependence can be defined in device tree or can be done dynamically as well. Power domains are responsible to notify all the devices using it when it changes its state. So when the domain is suspended, it goes through all children devices and asks them to turn off, call the action callback with the turn off action. And when the domain is resumed, it goes through all the children and with the action turn on. If you are using device runtime power management, the subsystem will automatically suspend and resume the domain as well if needed. So the domain, if the children need the application or someone needs to use a device, the device is using the runtime power management, this will automatically wake up or resume and suspend the domain if there is no one else using the domain. So the next few slides, the idea is to wrap up what is necessary to enable and implement power management in SOCs and also in drivers. So first things first, right? These are the 3 key config options that enable and disable power management features on Zephyr, basically. The first option, config PM, enables the system power management, the power management for SOC. And when this is enabled, the idle thread will call, the SOC APIs that was mentioned before. The next option is to enable device power management, because you make the device, make the system suspend and resume the device when the CPU is idle. Finally, there is this option to enable device runtime power management. The reason that we split, device runtime power management from the regular system managed power management is to save some resources. So if you're not using device runtime power management, there are a lot of data that doesn't need to be used. So we save some resources when doing that. And it's important to mention these options can all be combined. So you can use even the 2 methods to do device runtime, device power management. So when implementing power management for SOC, you have to implement these 2 functions, PM state set and the exit post operations. And if you're using the default policy manager, you have to declare the states in the device tree. So let me just make a point here. Declare power states in the device tree. It's not mandatory to execute the software. If you implement a custom policy, and you ensure that the states returned by your policy are known by the SOC, then you basically can return whatever you want. But it's really recommended to have supported states declared in the device tree, because this information would be widely available for all the rest of the system. Another thing to remember is that interruptions need to be restored after the exit operation, post operations. This is an example of how to define power state. First, you declare which power states are supported by the target with the appropriated information, and finally you have to set per CPU which power state should be used. In multi-core systems, you can have different set of states per CPU. Following up, if you want to implement your own policy manager, there are 2 things that have to be done. First, disable the default policy, and second, implement this function, the PM policy next state. The policy is where the power state constraints and latents are accounted. So you have to account these constraints that are imposed by other parts of the system and application. So if you're writing policy and want to use a state constraint and latest constraints, you have to check this in your own policy. On my left, you see the full policy implementation, and if you can note, it iterates in a reverse order, assuming that that is another thing that is important to mention. All the power states should be declared in the correct order. So from the shallow state, the deepest state, sleep state. And then checks if there is any lock for a specific state. If there is no lock, checks the latence, the exit latence for the state. If it's lower than the max latence, then finally, we just check the number of ticks for the next event, and we return this state. Okay, so to implement power management on the device, the very first thing to do is to implement the action callback. This callback can be called to suspend or resume the device when the system is idle, or doing device runtime power management. If the device is part of a power domain, it will also be called with when the domain is suspended or resumed. Then the next step is to define the power management infrastructure for the device using PM device define, or the device tree version, the PM device DT define for when you are using device tree to declare the device. The last step is to pass the previously created power management infrastructure to the device when defining the device. As you can see, there are macros to do this. If the device belongs to a power domain, it can be described in the device tree using a property for a power domain, or it can be later added to the domain using a runtime API, the PM device power domain add. For device runtime power management, there is no new API that needs to be implemented. What must be done is to make the device as much power aware, as much power as possible aware, suspend and resume devices itself when needed. Strategies about how to use this infrastructure really depends on the driver and the subsystem, or even in the application. The last piece, that I will cover implementation is power domains. They are, as was mentioned, just devices. There is no specific API for a power domain. That said, they are a special kind of devices when you are, implementing power management. The very first thing is that they have to declare as compatible with power domain in the device tree, or when you are, manually define the device. The other thing that power domains need to do is to notify all the devices that are under, them. There is a function helper to do this, so you iterate over the, children devices, and you call the action callback for these children. And there are much more about power management, other areas like if you're looking for device power management, you can set the device busy and change how it behaves for system power management or runtime power management. You can tune what is the initial state of a device. Device power management also, you have to worry about you can look for wake-up sources, define a device as wake-up source. You have APIs to turning the policy. You can add or remove latency requirements, and there are events that you can set. So there are many other areas, but that it's basically the general idea of the capabilities of the subsystem. And I think we are open for questions. Yeah.
Just sweet. So with device power management, there doesn't seem to be a huge amount of drivers actually implementing that, at least in the upstream tree. Do you have any ideas of how that situation can be sort of improved, or people can be incentivized, I guess, to implement that when submitting drivers?
Yeah, so the initial method for when power management was implemented on Zephyr, we had only the system management method, and that was and that it's the easiest one, that it's basically implement a callback. So most of the devices support this, but they don't support the runtime device power management that requires more effort. There are some devices that are doing this already, so I believe in that as soon as we have more use cases, more other devices will start following this.
First of all, great presentation, Flavio. Quick question for you. So, power management, the APIs are wonderful. The thing that I think some newer parts, and maybe even some of our own parts, clock scaling and trying to save power through clock scaling. Is that something that you've considered in the system power management APIs and such?
Yeah, you are talking about changing the clock frequency, and yeah, there are some plans to support this. Obviously, there is the complexity because then you have basically to go and notify, everyone that the clock has changed, so the device has to accommodate this. But there are plans to do that.
Are you considering adding that to the existing like power management APIs, or is this going to be, or is there some thought that this would be a separate clock tree configuration kind of thing?
So I believe I don't want to overload the API, the current power management API, at least the callback, to not become some I/O control API, like you have only one API with that does a lot of things. So probably this would be additional.
Great.
So this is a question actually for both probably Tom and Flavio. So Tom, I think you put in some device power management into some sensors. And so I'm curious how that plays with the runtime power management.
Yeah, that is a good question, and we've been talking about these. Sensors are definitely the most complex use case that we have right now, especially because they vary a lot and they have a lot of data, and there is calibration that they can lose if you suspended the sensor. So we are still grasping in this area. Duncan, as maintainer of the area.
Yeah, I'm a co-maintainer theirs, but yeah, we've definitely talked quite a bit about this. We had a great, in the sensor working group that we have going in the project, we had one of those meetings was dedicated to exactly this topic. The current API really is stateful, so you can set random attributes of a sensor. I'm going to set my sample rate. I'm going to set my range of readings. A lot of these sensors do take some time to start as well, so you don't necessarily want to be, constantly turning them off and on when it takes, 100 milliseconds to turn the thing back on and get back to where you were. So there's a lot to consider there, and but the kind of the consensus or close to consensus that I think we came to was that, in order to enable power management with sensors, they do need to sort of probably maintain the state that they had before turning them off, and then restore that state when turning them back on. Of course, the downside of that is now, all those attributes that were stored off on the sensor now need to be kept in your application's memory in Zephyr, which has a cost. But yeah, other than that, I mean, there's a newer API that might also help us here, because the current sensor API, we have this sort of ad hoc read, right? At any time after setting a bunch of attributes, you can just go, hey, go read my sensor. That's not really amenable to power management, right? So if I'm constantly, I set all my attributes, and then, I don't know, in a timer I go read my sensor once a millisecond, and then turn it off, turn it back on, turn it off, turn it back on. That's not really a great story in terms of managing time and resources and things. So.
I definitely don't see the sensors doing runtime power management in itself. Definitely they will have to collaborate with the subsystem, especially because there are several sensors that do these sequential calls for the sensor, and that doesn't make any sense, right? For the sensor to suspend and resume between these calls, knowing that they are sequential.
Jump in as long as nobody else needs to. Anyway, hi Flavio, how you doing? So this is sort of a little bit of a digression, but obviously in the context of the Meteor Lake DSP, there was something of a digression from the Zephyr Power Management Framework, where instead of suspending nicely from the idle thread, they had a pre-existing architecture which would do it under affirmative control, basically by a cross CPU IPC out of the host kernel and just saying suspend now, and of course that's exactly what it did. It entered a routine that did a ad hoc kind of DIY context switch, and I'm on the record as not being real thrilled with that. is it worth discussing anything that might be useful to the existing framework to try to maybe prevent that in the future, or guide systems to a cleaner API?
As far as I know, they are not doing this anymore. They are doing inside the idle thread when they are suspending.
Right.
So
Yeah,
they
exactly.
have a way to force the next state and basically bypass. But and they play a lot of tricks, right? And so that is one of the parts that I was talking about doing. So they basically disable some states for different cores and they let one core, be active at the time. So the framework is there and they are using and it's. I mean, as far as I know, it's working.
Right. Yeah. You
in some
can't
certain
make people
states,
do stuff. It was just a little bit of, I think, a learning curve for them, and I was wondering if there was anything to report or
Yeah.
otherwise.
So when I started using this, was there were a lot of hacks that they did in the SoC layer to check if the other CPUs were weak, and that was completely a mess. So they moved this upper layer, so the application now it's responsible to ensure that the policy will just select the most appropriate state for the CPU. So they put some constraint. They are starting using constraints for specific states and CPUs.
It's time.
Yeah. So thank you, everyone.
Check 1, 2. Hope that. We good to go? Hey everyone, good morning. Thank you for joining me here. I'm Disha Patel. I work at NXP Semiconductors. I'm a field application engineer specializing in MCU. I support all sorts of microcontrollers, and today's topic is Zephyr power management for wearable devices. So in this topic, we will understand more about designing low power using a smartwatch demo that was designed using like NXP microcontrollers. This demo will mostly help us understand how we can scale to like different hardware using Zephyr and use Zephyr capabilities. So in today's agenda, I'm going to cover smartwatch demo. We'll look at an actual demo. I have the hardware with me, but I'll show you a video instead. And you can visit our booth later to check out the actual demo. Then I'll jump into the power management of our NXP IDMX RT500 MCU, which is being used for this demo. This is to really understand how we include this in the Zephyr power management subsystem. So we'll go over that later. After that, we'll also go over the power optimization for display and graphics, which is really important. I'm going to discuss like most power optimization techniques, but for the display and graphics, it's like the most important. Apart from that, I'm also going to dive into like memory optimization techniques, which also help us extend battery life. And after the agenda, I also have like 5-10 minutes for Q&A, so please feel free to ask any questions that you might have. Thank you. So I'll go over the smartwatch demo overview, just so that you can understand what are the components of the demo. So let's see a quick overview before I play the video for you guys. The demo is based on Zephyr RTOS. It is highly power optimized for wearable devices, so that's why we thought of leveraging this for our demo. It leverages the features of power management of Zephyr and the actual silicon. So we'll see both Zephyr power subsystem and the RT500 subsystem that we have for NXP. The UI is created using the LVGL graphics library, which is an open source library integrated in Zephyr, and it can be easily used with it. In addition to that, we also have a GUI guider tool, which is an NXP tool that helps you design graphics for the smartwatch screens, which generate code for LVGL, and it supports the UI for the demo. Going a bit over the demo hardware. So I talked a lot about the RT500 microcontroller. So we have an evaluation board, like an eval kit that we call an EVK for the RT500. That's the top picture. And along with that, we also have like a smart display that you can order off shelf from our website as well. So for RT500, it's based on a ARM Cortex M33 core. And it also has a Cadence Extensor DSP, which is enabled with a 2D GPU. So it has a lot of features. I'll just cover the key features that we are going to use for this demo. The key features for RT500 in this demo are the power management optimization that comes with the MCU. The MCU also has like a dynamic power scale, voltage scaling PVT sensor that we are going to use. Then we have the 2D GPU for vector graphics acceleration. It also comes with a smart DMA that transfers frame buffers to MIPI DSI. That helps us further reduce power. We also have a 5 MB tightly coupled SRAM on this part, so that enables us to use a lot of memory that's required for configuring like a smartwatch which is heavy on graphics. And it has like a execute in place flash as well to accompany with it. The demo is actually available on GitHub, so we constantly make changes to it and upstream to it. So after this session, you can actually go on GitHub and try to include this demo on your hardware or even like use RT500. I've shared the link at the end of the session, so we'll go over that later. So coming to the actual good stuff, the demo video. So let me just, I hope it lets me do that. Yeah. Oops. I just switched between screens. Okay. Still don't see it. I tried that earlier. I could switch it before. I don't know. Yeah, the display is gone. Sorry about that. Do you have any questions so far about the demo, about RT500, about saving power on wearable devices with Zephyr? None so far? Oh, thank you. So I'll just back up a little. So this is how it's connected with the RT500, the screen I mentioned before. And now we are going to see what the actual demo looks like. This is the startup screen. And we have a digital watch screen and an analog watch screen that renders using the GPU. Along with that, we have a lot of animations. So this is the weather animation with like a lot of background animations with the clouds and stuff. This is a static display of a fitness face of a watch that we have like regularly on our screens. This is the EKG. This might consume a lot of power because it's kind of always on. So we'll look into that later. The music face has 2 song selections. So we'll be able to see that in a second. So it actually tries to mimic an actual smartwatch. And that's the home screen again. That's the demo. I have that demo with me if anyone's interested in looking at it later. And that's the 2 faces that I showed on the screen. So in this session, we are going to, as I previously mentioned, we are going to discuss different power saving techniques, most of which are based on one of any of these 3 key techniques. So for the first one being reducing power in active mode. So as you can see, let me turn on the cursor here. As you can see, we'll be looking at reducing power and current when the watch faces are active. We'll also be looking for reducing current when the watch faces are in like idle mode. We'll try to take them into a deep sleep mode so that we can reduce power even in idle mode along with the active mode. And the third point would be reducing duration in active mode. So if a watch face it's just idle, we don't want it to be there as often. We can just reduce the duration of that particular watch face and save power in the active mode. We have multiple power optimization techniques, and configuring them separately with kconfig symbols helps us do that. So we'll talk about this slide often comparatively with the techniques that I'm going to share with you. Those mostly consist of the kconfig symbols. And depending on how you turn them on and off, you can save power in any of these 3 ways. So a little about power management of the ADAMX RT500 first, just so that we understand how we include the Zephyr power subsystem within it. The power management of the RT500 will obviously affect the power optimization of the entire demo. We'll just be focusing on the core voltage supply of this chip, which supports dynamic voltage and frequency scaling. So our demo basically works on 192 megahertz frequency and a 0.9 volt, but you can dynamically scale it as per your requirements. We can, based on it, we can run it on faster or lower frequencies and reduce or increase the voltage accordingly to save as much power as required. So these are the RT500 power modes. Our demo focuses just on the first 3 modes. We're not going to look at the last one. In the active mode that's on the top, consumes the highest amount of power. All the peripherals are powered, the entire MCU is functional at this point, so you're looking at something that's highly, not power efficient. So we also have our sleep modes for that. So the sleep mode, the second one, it's good for an ideal state. If you want your smartwatch to work in an idle state, in the RTOS, most of the MCU peripherals would be functional, but most of them you can switch it off and also retain memory. The next one would be the deep sleep mode. The deep sleep mode is much low powered than the sleep mode. The current consumptions drop significantly. So if you see the 4th table there, the VDD core data sheet, so compared with the sleep mode, it's up to like 11 milliamperes. But in the deep sleep, it goes to about like 20 to 52 microamps. So that's like a significant current, like you can save a lot of current there. So that's basically the deep sleep mode is one of our most popular ones that we leverage in this watch demo. And that also helps us with the memory retention. So that's the reason why we are not covering the full deep power down mode here, because it doesn't have memory retention. So we are going to skip that for this smartwatch demo. Along with the RT500, we are also using a PMIC, a power management IC, that we designed practically for this MCU, the RT500. It is a power management integrated circuit, and the part number is the PCA9420. It has 4 regulators, 2 switching, and 2 LDOs. So, and it also has 2 PMIC mode pins. So if you see those green from the bottom, the PMIC mode 0 and the 1, those PMIC mode pins help us change the power states that we saw earlier. So the sleep and the deep power down. So 2 PMIC mode pins, that's 4 combinations of sleep modes. The MCU toggles these pins, and the PMIC will update the voltage regulators to supply a specific power. These PMIC pins give us 4 power states that we saw earlier, and we basically leverage those into our demo. So now that we know the PMIC, moving on, that was basically all for the power management of the RT500, the PMIC and all the features that we saw. So now moving forward to the Zephyr power management subsystem. So the Zephyr power management subsystem is called a PM subsystem, and this is the kconfig that enables it. So if you can see the kconfig on top, the config PM, it really helps you enable the Zephyr power management subsystem that you can use in the demo that you're working on. It's divided into system and device power management, and we're leveraging both in this demo. The system power management affects the entire SoC. So in idle states, it will determine changing the SoC states. Basically, the kernel enters the idle state when it has like nothing to schedule. So enabling this kconfig PM allows the kernel to like call upon the power management subsystem and put the idle system into one of the MCU supported power systems. In the device power management, the way it works with nodes within the device tree of the RT500. That is like various drivers, components, and applications. So these are 2 different subsystems, but we kind of leverage both of them in our demo. Going forward, we saw the PMIC earlier, so I felt it would be good to show you a snippet of the device tree from our board file in Zephyr that shows how the PMIC is configured at build time. So the regulators that I mentioned before, the PMIC mode pins I mentioned before, you can see there are nodes in the device tree for each of the regulator, and it has different settings within it. These power states generated by the PMIC are also leveraged in our demo. I'm not going to go in details of each of the settings, but this should give you a good picture of how a PMIC can be set up in the device tree to save more power. Moving ahead, this is also an example of the system power management that I was talking before. So in the PM subsystem within the device tree on the SoC level, there are defined nodes in the power states. So if you can see, there's an example. So on my left-hand side, you can see power states within the device tree are the idle state and the suspend state. So it's runtime idle and suspend to idle. That's the name of the actual power states. So they can be translated into our shim driver within the RT500, where Zephyr calls the idle mode when the power state is idle. And it calls the enters deep sleep when it's in suspend mode. So it basically tries to see which state has been called within Zephyr, and it calls the same state for the RT500 itself. It basically translates what's in the Zephyr subsystem to the RT500 actual powered mode in the shim driver. As I had shown a graph before where we saw those key key techniques that we can save power. So one of them, the first one I mentioned was the reducing power in active mode. And this is an example of reducing power in the idle mode. In this demo, the watch faces are in the idle mode most of the times. They wake up once in a while, they just render a new screen, a new time, or like a new update that they have to show on the watch screen, and then they go back to sleep. So this is a good way that the demo actually leverages the Zephyr power management subsystem. So it enables the tickless low power modes when the application enters idle task. This leads it to enter the deep sleep static mode, while the idle, it's idle for, say, at least for like 620 microseconds. There's a bit of a calculation with the 620 microseconds, but I'm not going into that for this session, but you can check out the actual GitHub repository for this and the example. And so this device, like in this demo, it either enters the deep sleep, or otherwise then it will go to the normal sleep mode. Zephyr's power management subsystem also enables the drivers and app to lock out of any specific low power modes. So we saw like we are not using the deep power down. So you can also try to block some of the states. You can only use a few of them. In doing this, as I mentioned before, we are enabling various K-configs. So earlier we saw the K-config for the actual power management. In this, we have the K-config enabled as well. And by enabling this, we compared our results with, while enabling it and disabling it. So we can see that graph right there at the bottom. So this graph basically it shows how a watch face just is awake at a time to just render the new face, and then it goes in idle mode. So by configuring this K-config, we can reduce power for the specific analog watch screen by 95% compared to when it's disabled. So that's a huge difference you can just make with like a one K-config setting. I'll also talk about the dynamic voltage scaling using a PVT sensor. So this is a good example of reducing power in active mode. So we saw reducing power in idle mode. The PVT sensor that is integrated within the RT500, that's a good example of seeing how you can use actually available hardware to your advantage. So it might not be on any of the microcontrollers that you use, but this is a good example of how to use Zephyr with this existing PVT sensor that's integrated within our RT500. This is, again, brief explanation. But if you are really interested in knowing how the PVT sensor works, there's also a link available. That's like a 20-minute video of the working of the PVT sensor itself. And that's a training, so that can be helpful as well. So the PVT sensor, basically what it does, it allows us to optimize the VDD core voltage that we use to supply the chip that we saw earlier. It runs on a voltage control loop. So if you see the block diagram, it runs on a voltage control loop based on the temperature. So ideally, the best case scenario in this case would be, say, running the smartwatch demo on room temperature. It basically optimizes the process voltage and temperature variation, and I won't go deep into the graph there, but it basically is a loop, so it corrects itself and tries to provide the exact voltage that's required during like a particular temperature that the demo is running at. So that was mostly our power management system for RT500 and the Zephyr subsystem. I would also like to talk about the power optimization techniques, as I mentioned before. I showed you most of the power management techniques, but I would like to focus on the display and graphics, because as a smartwatch demo, the most of the power is consumed by these two factors. So I feel like this would be really helpful for you to understand how you can implement it at your level. So I showed the demo before. We are using a MIPI smart panel display. It's a smart display, and we only need to talk to the display while updating the screen. On the MCU, the RT500 side, we have a GPU rendering. We have a GPU that's like rendering images. We are also leveraging the smart DMA that's within the RT500, which efficiently reads the data from the frame buffer, and that eventually leads to reducing more power. And on the graphics side, I'll talk about the reducing duration in active mode. So the figure on the right top corner, I mentioned before the key techniques. So one of the key techniques was reducing the duration. So this is how we do it. We already saw reducing power in idle and active mode. This is a way to reduce duration in the active mode. So the GPU that's built into the RT500, it uses 2D vector graphics acceleration, and it's enabled by NXP's Visualite driver that's ported to LVGL. So it's highly optimized for any kind of like power-sensitive applications. It helps the offload the CPU to do other tasks on the smartwatch. So it's a great way to basically offload all the graphics capabilities from the actual CPU that's going to be, say, in like sleep mode, or you want to be active. So that's a great way to save power. And for doing this, we have another kconfig. So we're using the kconfig that's highlighted in blue. And we have, again, made a comparison of when the kconfig is off and when we turn it on. And the difference that we've seen is it reduces the analog watch screen power by 14%. So that's a significant decrease for a graphics kind of application. So that's how you can save more power on graphics and a display compared to when you're not using the kconfigs or using the Zephyr power subsystem. These were the power optimization techniques. I would also like to talk about the memory optimization techniques, because they are also important in terms of reducing power. And that's basically for extending the battery life. So that's our goal for the session here. Minimizing, so the first technique would be minimizing the accessing of external memories. So the RT500, the MCU part itself, is a flashless device. and it operates on external memory. So it consumes more power, and it's better that we would, if we are able to make use of the SRAM, the internal SRAM, that would be better for us to save power. And the SRAM for this part is flexible up to 5 MB, so we can leverage that to our disposal and save more power. And we do that again by configuring a few of the K-configs that are available. So I won't go into the details of the features itself, but I'd like to highlight that just by changing one K-config for accessing, making it not access the external memories, we can save up to 8% on the digital watt screen power by that much. So I think that's a significant power save move here, just by not trying to access external memories and just trying to leverage what hardware we already have. So the second technique, the second memory optimization technique I would like to talk about for power, for saving power would be relocating from flash to SRAM. So we saw how we can save power by just not actually trying to use the external memory, but we can also see how we can relocate the contents of the flash to SRAM. So that's how you do it in detail. And accessing, we have already discussed, like accessing external flash would consume more power compared to the internal SRAM. So when you actually turn on the K-config here, it leverages the large internal SRAM. The smartwatch app is kind of too huge to be actually moved from flash to SRAM. So we can do that in like different memory sections. So we'll make use of the SRAM code regions and put all the executable code there. And we will see the details going ahead. Sorry. Yeah. So I won't go into the details of this, but if you are looking for relocating all your SRAM details, this is the way you do it. We've already discussed the different K-configs, but you can actually use the Zephyr code relocate to use the read-only data for all images kept in flash. So you can follow these steps. You can configure your linker script to do that. So that's a great way that you can use the RT500 to do that. This is the third memory optimization technique. So this reduces power in active and idle mode. So it's basically the RT500 has 32 partitions within the SRAM, ranging from 32 to 256 KB, depending on how much SRAM availability is there. So each partition in itself can be turned off in different modes, and you can actually disable the bus access. So this is a great way of trying to see which RAM partitions are actually unused. And when you get rid of those memory partitions, it will be easier to save power. So it helps in reducing power in active mode. It also helps reducing static retention power in deep sleep mode. The demo has a release mode, which uses like less SRAM and it powers off the unused partitions. So you wouldn't have to use all the SRAM available and just increase power. So the way to do that is enabling the K-config, the K-config smartwatch reduce RAM. And we've seen in our observations that we can reduce the analog watch power screen by 18% compared to when it's off and compared to when we actually turn it on for our demo. So that was the recap of the power optimization techniques and the memory optimization techniques. So I would like you to remember the key takeaways for the demo, apart from the demo video. So we saw a lot of K-configs during the time, so I've listed it for you here. You can use most of these. You can, this is basically for the RT500, but you can use it for other MCUs as well. And to summarize, I really want to focus on the power savings. So we can see there's a table right there that shows us how we can, shows us how much power we actually saved in percentage when we turned on the K-configs compared to when we didn't. And this is all reduced power or like reduced duration in active and idle modes. And this is basically to show how we can leverage different kind of controls within the MCU, within the hardware that you're using, just using the K-configs or making edits to the device tree. So that's a really good example of seeing a smartwatch demo, which is usually a very power-hungry application. So that's a really great way to reduce power there. As I mentioned before, I've also added additional resources. So that would be the link for the smartwatch demo repository. I think this slide deck would be on the website, so you can reach out to us. You can check out the actual repository. You can order the RT500 and the display. It's off shelf. It's available on our website. So you can practically make this demo on your own. Thank you. So Q&A, I think we have about like 8 minutes. Sorry, I took up 2 more minutes. Any questions, any comments? Yeah, you can go ahead.
Thank you very much. I had a couple of questions about the RAM usage, copying the flash into RAM. You're using a custom bootloader. Does Zephyr have the ability to do that automatically without a custom bootloader?
Right, yeah.
It can do that without a bootloader?
Yes.
Okay, great. The other one was shutting off the RAM. Does it know which banks to shut off itself, or do you have to provide a linker script or something that shows which ones are available?
Right. So you'll have to configure the SRAM. So you'll have to, from the datasheet, you'll have to know the exact RAM partitions that you're looking for.
Okay.
Yes.
So Zephyr can't say, I'm only using X amount, I can shut off the top ones.
Right. So
Okay.
yeah, within the memory, like if you look at the partitions, you can see which ones are not using as much. You can get away with like shutting off power to those memory partitions, and that's the way you would do it.
Okay, so like you look at the map file and then decide which ones to switch off. Perfect, thank you very much.
Thank you so much. Any other questions?
Hello. I was wondering if you noticed any significant performance changes after you made these optimizations for power.
Right.
And specifically, I was kind of wondering if moving all of the flash into memory actually resulted in a performance boost, because you mentioned spending less time in the high power consumption mode.
Right. So I know I mentioned those in like percentages, but I might have like some backup slides for the actual current consumption for the specific RAM. So these are the power consumption numbers and the graphs for PVT. Yeah, so this is the SRAM, it should be somewhere here. Oh yeah, I don't have the slide for that, but we can discuss later. Maybe I can show you the actual power saving numbers. I know like percentages don't do justice to the demo, but yeah, we have some current and measurements for you to actually compare. Any other questions? Thank you.
So I'm making a few assumptions here, but it seems like some of those features, like the PVT sensor and stuff, are like architectural SoC level features, but the like the K-configs seem to be like application scoped. Is there a reason why that's not like a system on chip level option?
So in like this demo, I was trying to actually demonstrate how we can use the already available hardware. So if you have a different hardware, you can try to leverage those hardware features using Zephyr. So that was kind of the goal of the.
I meant for like the RT500 has
Oh,
the PVT
okay.
has the PVT sensor.
Right.
I'm assuming, but it looks like you're turning that on at like the application level. Like it's the config is smartwatch PVT enable. Is that in the application or is it in the like the system on chip code somewhere?
It's in the application.
Okay.
Right. Yeah. The application uses the system on chip. It leverages those features or key features that's in the PVT sensor. Yeah. But for that, you would also have to know the working of the PVT sensor in the RT500 itself. Yeah, that's right. That's a prerequisite. Yeah. Any other questions? Anyone would like to see the demo that we have?
I had one question. Is there any wireless implemented with the smartwatch?
Not yet.
Not yet. Okay.
Yeah. Are we looking for any updates?
Any BLE or Wi-Fi?
We are doing like Zephyr enablement with the Wi-Fi, but with the demo itself, we have not integrated it. It's mostly like a demonstration, so it shows you capabilities of what the demo can do. But yeah, the other peripherals, Bluetooth, we have not included in that. It's not a real smartwatch yet.
Thanks.
Sorry?
Does it have radio peripherals?
No, not yet. Yeah, it's just the screens and the display that we
Sorry,
should.
the RT500 itself, does it have a Wi-Fi processor or a BLE?
So the
or?
RT500, it's a basic MCU, but you can pair it with our other Wi-Fi part numbers, the IW612. So that's already integrated. Yes.
Thanks.
Thanks.
Just a question about that PVT loop. I was wondering, how is it configured? Basically, where does that logic reside? How does it know? What does it say if operating limits? What are the temperature slopes? How to compensate for them? Where is that part implemented, and how is it configured?
So it's in the application code, but in the device tree also it's enabled. Yeah. Derek,
So-
would you like to add more to that?
So the PVT sensor is a block that manages or monitors your timing loop of your critical paths based on the current operating temperature and frequency. So when it sees that the timing margin is decreasing to a point where it might get to be an issue, it interrupts the application to request a higher voltage. And then the details to configure all that get pretty deep. And the link that she shared has an app node and a video and a link to our, we call it an application software pack with the driver to leverage it. Thank you.
Any other questions about NXP apart from the smartwatch demo, about any microcontrollers you're interested in? Yeah, that's all. Thank you so much for coming today. Thank you. Have a nice one. And please later. Yeah, thanks.
welcome attendees. Keynotes will begin shortly. A reminder to please silence all mobile devices and take your seats. Thank you. Attendees, please welcome to the stage Kate Stewart, Zephyr. Please welcome to the stage Kate Stewart, Zephyr Project Developer Summit Program Chair, and Tim Bird, Embedded Linux Conference Chair.
And I'm hoping that I make it with you.
Please welcome to the stage Kate Stewart, Zephyr Project Developer Summit Program Chair, and Tim Bird, Embedded Linux Conference Chair.
Hey! Great to see everyone here. Welcome to Embedded Open Source Summit 2024. I'm seeing a lot of familiar faces that I saw in Prague, and so glad to have you back here. And we're excited to be with you now in Seattle. So before we get our program started this morning, first, want to make sure we have huge thanks to our diamond sponsor, Intel, and our other diamond sponsor, Texas Instruments. We would not have been able to make this event possible without your help, and it's very much appreciated. As well, I want to thank our platinum sponsor, Midokura. So, like I say, we would not be here without your support, and so we very much appreciate it. And also, thank you very much to our program committee, who did an amazing job with their curation and reviews, and I think we've got a pretty good set of content for this event.
So we have just a little bit of housekeeping that we'd like to go through before we start the keynotes themselves. We encourage you to visit the Solutions Showcase. That's in the ballroom number 1, located on level 5, same level as this. It's just over in the other section of the building. You can find coffee breaks there daily, as well as lounge area activities, job board, and a whole lot more. And the sponsors have a ton of information they want to share with you, and a lot of interesting stuff. In terms of Wi-Fi, on your lanyard, on the back of it, if you look at it, your badge, there is Wi-Fi information. There's also Wi-Fi information scattered throughout the building. So the last thing that I want to talk about is we do have lunches included every day of the event. And in particular, there's a women and non-binary lunch, women and non-binary and open source lunch. That's today at 12:55, and that's open to all attendees who identify as women or non-binary. There's no pre-registration required, so if you're interested in that and qualify, then please feel free to join that. The lunch will be located in Terrace Suite 2, and that's on level 4.
I'll look forward to seeing some of you there. During the afternoon break, we'll have our Ask the Expert session, and it's a good opportunity to talk one-on-one with some of the longtime community leaders in our area and get advice, ask questions, and more. These are at 2:55 today and are in the Solutions Showcase, so back in the trade flow area, bar area. And it's the Olympic View Lounge on level 5 as well. So, and also, tonight in the sponsor showcase, don't miss our Tux track, where it's going to be looking at, giving you a chance to network with your peers and ask questions about the sponsors and check out their trends. And so that will be beginning at 5 o'clock today, as soon as our sessions conclude.
Okay, so that's tonight. And then tomorrow night, we have our receptions, and we actually have 2 different locations where you can choose to go. You can go to the Garage Billiards and Bowl, or you can go to Stoop Brewing. Just a note on the Garage Billiards and Bowl. Both of those locations are about an 18-minute walk, which is not too bad, but if you would rather not walk it, there will be transportation provided. And the Garage Billiards and Bowl is limited to attendees who are 21 years and older. And you will be required to show a government ID to get into that, but that will have some fun stuff going on there. At the Stoop Brewing, Capitol Hill, that is open to all attendees, all ages. And those begin at 6 p.m. Make sure you have your badge so that you can attend those. And then the last thing that we want to just remind everybody of is our event code of conduct. We want to make sure that everyone feels welcome and included, and we just want to have respect and a high degree of professionalism here. If you have any concerns, if you see anything that concerns you, just please go to the registration desk or talk to any member of the event staff. And there's also an info desk in the Solutions Showcase area, and they'd be happy to talk to you about anything that you have that's a concern. With that, let's go ahead and get started. So this is going to be a little bit weird because Kate and I are co-introducing each other. Our first speaker today is Kate Stewart. And besides being the being on the Embedded Open Source Summit program chair, she's the chair, Kate is also the vice president of the Dependable Embedded Linux Systems at the Linux Foundation. So Kate has launched a number of projects, including ELISA and Zephyr projects, and she's involved with Real-Time and many other embedded projects. And today, Kate is going to talk about some of the challenges involved with open source software projects that are used in critical systems. So Kate, thank you.
Thank you. Okay. Actually, I adhere to the Steve Rosted rule of slides, so you're going to be seeing a lot of slides go by very quickly. Do not freak out, they'll be posted, okay? But open source is pretty much everywhere. And to illustrate this, let's consider something we want to be safe, a car. More of the components in these cars these days are built on open source every year. We've seen it start with AGL and for the infotainment systems, but it's moving more and more into the drivetrains, more and more into the safety critical aspects. So they're likely to have cameras now embedded on them to help the driver see backup and side views. There's also radar sensors to measure distances and provide alerts when you get too close to another object. This information helps keep the driver and the passenger safe. So far we're in the traditional embedded space, but in addition to the proximity information, you're also going to see dashboards that are incorporating navigational assists that help the drivers get to the destination faster using GPS technologies and communicating with external services to understand how things are like with traffic conditions. And again, this information keeps drivers and passengers safe and helps you arrive at your destination sooner, so it's all a good thing. And as we're moving towards autonomous systems, the LiDAR and the other sensors are now being incorporated. And there's also the need to filter this information and react appropriately to what you detect. And so if you don't have the human evaluating the input, as it seems, you're training these AI models. And you are working to get these with the connected sensors to actually start to look at data sets to how this all fits together. These inputs from the multiple sensors need to be coordinated. And the data training sets are going to be really key to making sure it recognizes the right things. So all this information is going to be needed to keep the driver, the passengers, and the pedestrians around the driver safe, because that's a 2-ton piece of hardware. So what are the ingredients for a modern car? Now we're no longer just hardware and software, we're also training data sets and we're communication to remote services. So all of this stuff is sitting there, and we have effectively ways of starting to summarize it, but they aren't talking to each other. And so we can't reason about them. So let's take a look at what's happening in the industry right now. There's an AI incident database out there that's open to everyone, and it looks at what was happening. And this is from 2023. These are some of the instances I pulled down for self-driving cars. And 3 of the 4 are Teslas, so I'm going to focus on the first one. And if you look at 550, which is that first one, we get a link to the full story on the Washington Post, and they did a really good piece of reporting on it. Basically, it contains concerning information such as not recognizing school bus signs. It's not being trained to handle interactions with motorcycles and emergency vehicles. There's now over 8,000 vehicles on the road with autopilot capability, okay? And almost half of them have had to be recalled to fix recognition of things like traffic lights, stop signs, and speed limits for the autopilot and driver assist. And so we also know from Tesla's press they're running Linux on these cars. So there is safety aspects being used here, even if we're not, when we're designing Linux, thinking about it. And the other thing is, in the last year, self-driving capability expanded from 12,000 to over 400,000. And 2/3 of all the reported incidents last year were from Tesla because of that expansion, because other car makers are doing a little bit less aggressive of a rollout of the technologies. And then Tesla recently tried to eliminate one of the radar sensors for economic reasons, i.e. shrink down the cost. And they found the crashes were too high because the model couldn't compensate. They actually didn't need that sensor. And so they reintroduced it back into future products, and they hopefully have turned it back on those who have it. So from a self-driving car, there's more ways things can go wrong now. We've got the hardware, the software, the data, the communication services. These are all ingredients. And they all need to potentially play a role of interacting with each other to understand if you're going to be safe, or if there's a vulnerability, can you fix it? But this isn't just in cars. Consider your operating room in a hospital these days. an increasing portion of these devices are also running open source, and failures could have an impact on a person's life. And one of the things that we're seeing is that the FDA is recognizing this, and this is why there's been a big push behind the SBOM initiatives, basically trying to expect to see system-level information. So not only the SBOM, but the device and the related systems before things get deployed and get the approval to be deployed. And this is also there sitting in critical infrastructure. So the critical infrastructure today needs this transparency, and they're using open source throughout a wide range of it. So what we need to start looking at is, okay, how can we start to manage risk and ensure the safe usage of interactions, all these ingredients, including the open source? So not just, the Linux kernel is, 1 commit an hour of a bug fix, right? These systems and so forth, are, it's a different impedance mismatch, and we have to watch out for the safety side of it now too. So Japan, 2 years ago, in mid-2022, basically recognized for cybersecurity action plan, you need to focus on the safety profile. And so the question became is how? How do we do that? Well, there are standards for safety critical systems. They've been around for 40 years. And they know how to minimize and mitigate system faults. And part of the challenge is going to be that SBOMs are going to be used to improve the what's known. The transparency of what's known is what SBOMs are conveying now. And so you'll be seeing more of that happening. And today, when people are doing the analysis and trying to apply a security fix, it tends to be a lot of those types of spreadsheets and paper files and everything else. And we need to automate this. We need to get it faster so that people can actually do the relationships to understand how things are interacting and can we have safe usage. We need to be systematic about it all. So we pretty much need to start thinking from a software bomb to a whole system bomb. And certainly on the hardware side, they're used to bomb concepts for a long, long time now. So there's no surprise there, but we're not talking the software bombs linking to the software, to the hardware, linking to a firmware, linking to various versions of everything. And so all these ingredients need to be considered. So getting standardized metadata in the supply chains is going to be the big challenge. What software is running on hardware, specific hardware, what components are the dependencies, the software training models, if that's in there, what are the data sets for evolution risk. We need to have a clear understanding of the service APIs. All of these are pieces that could have an impact on the safety as well as the security. And we also need it to be accurate, garbage in, garbage out, right? And because we want to start catching the information when it's created. When you're designing something, keep the information there. When you actually put the sources, build the sources, all of that information is accurate when you're sort of working with it, but trying to discover it afterwards is really, really hard. So there's work going on to basically support generating these SBOMs when the facts are known, at least. And we're lining up pretty much what's been going on from CISA with some standard definitions of what this means for a type of SBOM, what sort of information should be in there. And one of the other projects I work with is SPDX, and we've been evolving the framework to be able to connect the metadata about components, processes, requirements, and evidence, so we can actually do product line management. And it was announced today we have SPDX 3.0 out, and so that is actually our starting part for being able to do this analysis at scale. We've got the notion of various profiles that are affiliating with type of knowledge domains, like software, obviously, like AI and ML models, like dataset. If there's sensitive personal information, you want to record that, because that's another factor of a risk. And then we're going to be extending beyond to pretty much basically be going in the SPDX 3.1, looking at what's happening with hardware, what's happening with services, operations, and then finally having a true safety profile so we can automate all this. You're going like, okay, we can automate all this? Well, actually, I think we can. There's a broad, in SPDX 3.0, we've got the core and software licensing and light, and that's what we had in 2.3. And we added in the AI data build, because in safety, we have to understand how everything was built. The supply chain is critical, as well as the security, because we need to understand, are there vulnerabilities, known vulnerabilities, et cetera. So we're sort of moving in that direction, but we have to connect these components, and in SPDX 3, we have a wide set of relationships for connecting one component to another component. And so this is basically, we had requirements of, we had specification of, we had it for 2.3, we're carrying it forward, so we can start to hook the requirements in with the code, in with the tests, in with the evidence. If we can start to hook these all together, we start to have something that we can automate and put into a database and a knowledge graph so we can be querying it. So SPDX3 is pretty much extending beyond what we've got and bringing in things like being able to do digital twins, FPGAs. How can we have the other hardware? And there's various external services. So you'll be seeing things emerge there, and if you're interested, we can talk more later. But it does support the modularity and the relationships that we can get this knowledge graph going. And if we can start getting knowledge graphs going in companies, so that when they're having to remediate, they can also spit out the SBOMs that they need at a time, as well as do the analysis for their safety cases. And the way something like this could work, and then I've been working with some of the, Nicole, who's been my partner in crime on this one, to basically say, oh, these SBOM types, there's information there for the safety cases that we want to use, which then lets us actually go and actually map the V model into evidence that we can start to work from, which then lets us look at, oh, we've got a design SBOM, we've got our safety case. Oh, hey, that gives you information and the specification for your coding guidelines, which are part of your requirements, and so forth. And so you can use these relationships to hook things together. And then, when you've built it, you've deployed it, you've tested it, you've got evidence. So when there's a bug, and you know there's a bug in your binary, you start to have a way now to basically figure your way out. Did it come in from my supply chain? Did the bug come in from my source code? Oh, it came in from the source code. Did it come in from the coding guidelines problem, or did it come in from my requirements? And this starts to let us actually trace back how we can figure out where the real problem is. And that's what's missing today. And we can take within a code base, we can actually go and do requirements within actually a component and actually start to map the requirements to the code to the tests. And we've done some prototyping of this by logging things through in Zephyr historically, and we're working on toward to get this going. And the nice thing about if we can get this requirements going to the code to the test, suddenly when you can say if there's a bug, you can actually be explicit and know there's a bug, and you can say which requirements it came from, or potentially do we have to create a new requirement, new tests, and create the evidence and satisfy your safety case. And so this is a way we might be able to finally get after automating safety profiles. And so this also means, one piece of code may participate in multiple requirements. We can trace that too. So how do we establish this with open source projects? Well, there's 4 projects I'm working with here at the Linux Foundation that are taking parts of it, okay? The ELISA project is working with Linux, and we're trying to increase how we can work with the difference between a kernel that changes 9 commits an hour and a safety community that is expecting maybe 1 commit update a year. And there's a variety of working groups tackling aspects of all of this, and basically we're focusing on the Linux-based systems, and we are working forward from that. There's a systems working group that's putting together a reference system in the open, because everything in safety happens behind closed doors and NDAs out there, or a good part of it anyhow. And they're busy putting together Linux, Zephyr, Zen, and with Yocto. So we have a reference build of everything that we're doing it in the open. So we can start to analyze the system cases, look at the SBOMs, things like that, prototype it. And that open integration is certainly all part of it. And we sort of working forward from there. The other thing I just want to highlight is Red Hat just open sourced last year this tool called Bazel for requirements tracking. And what it's trying to do is look at the requirements of the kernels and start to hook everything up. And so if you're interested, there'll be a talk on that on Thursday. And Luigi and Gab are here to talk about what's going on with that tool. And so we'll be looking at that and using that for Linux. The other project is Zephyr, where the Zephyr's mission has been, right from the start, to support safety and security for resource-constrained devices. And Zephyr is basically trying to focus on going after initial certification for 61508 SIL 3 and 26262 ASIL D is on the horizon potentially as well. And so we're basically defining a limited scope for the kernel and then trying to get that traceability going. And with this project, we're using a tool called StrictDoc and looking at a hierarchical structure of requirements for the project, and there's work going on for satisfying the requirements. And StrictDoc is working to import and export from SPDX, as is Bazel. The third project is Zen, and that's bringing virtualization everywhere. People are familiar with Zen for hypervisors. It also is neutral governance and so forth. And today, what's happening is Zen is working to improve their coding style with Muser C, and it's implementing various features. But the project members are also working on getting Zen certified, for 61508, and they're using OpenFastTrace as a tool. And they're trying to align to use SPDX. So eventually we'll have SPDX going in and out of all these tools, and so that we can start to hook up all up together as a system and import these SPDX systems for the system, say, oh, I'm using the Zen, I need these requirements, I can hook this together. So that's kind of how it's going. And then we've got Yocto, which is actually creating a reproducible build system already, and is fairly commonly out there for most of the embedded space. I think we've got a lot of Yocto fans here in the audience. And so we've got SPDX 2.3 SBOMs already with Yocto, and it's been there for a couple of years. And we're participating in the creation of the SPDX 3 build profile for the things that they wanted. So with that, we've got Yocto support sitting there. They've been working on the product line System Bomb with SPDX 3. It'll be rolling out sometime in the next year or so. And so Joshua Watt's here, and if you get a chance to chat with him, he can give you more details of the plan. So those are the projects I know they're sort of trying to tackle this and put this together in a full system. And these are the pieces that are going there. So, integrating this open source efficiently into system engineering is overdue. There is a path forward, but obviously a community is going to be required. And one of the things Greg has been very clear to me about is, don't expect the upstream project maintainers to take the load here. We're going to need a community of people, and hopefully we'll get the maintainers to review what we're creating and to get the evidence available so that other people can share it. And so the next steps in the discussion, we've got a safety critical software summit on Thursday. If you're interested in this topic, please attend some of these talks. And then there's various, we got a thing, but we've got various project links. I will be uploading these slides after I get to my computer. And you're welcome to join any of those projects and their safety groups, or join the SPDX project if you care about the safety profile as a whole. And with that, that's kind of what I had to talk to you about. I'm a little bit over, but hopefully I'm close. So, next, I'd like to welcome up the stage Anas Nashif. Anas is our principal software engineer at Intel, and he's also our technical steering committee in Zephyr. He's a committee chair in Zephyr, so he'll be discussing the distinction between product and upstream development using Zephyr. And with that, I will turn it over. Please welcome him.
Thank you, Kate. Thank you, Kate. That was very interesting, yeah. So I will be talking, this is obviously, based on the title, I'm not promoting a product in this case. I'm just talking about Zephyr and trying to highlight how important neutrality in open source projects and the efforts we have to go through on a daily basis almost to keep the project open for everyone, trying to avoid dominance. We have a lot of companies participating in the project, delivering their own products and so on. And we always have to go through the effort and making sure through our processes, through our guidelines, through everything that we have in the project, making sure that everybody is treated the same. There is no, as a developer, as a user of Zephyr, you don't have any disadvantage because somebody else is doing things or treating Zephyr in a different way. So I guess by now you heard a lot about Zephyr. We are in the Zephyr Developer Summit talking about Zephyr features, Zephyr infrastructure, Zephyr plans, releases, developers, and the community as a whole. And one thing to understand in looking at Zephyr and what Zephyr is trying to do is the fact that it actually came out of a product almost 10 years ago. Yeah, it basically something that we took from a product and we tried to convert into something that is suitable for open source, and strengthening that even more by inviting different industry leaders and companies to join the effort to make sure that it is not perceived as yet another product that is just, releasing its source. And that actually went really well, and we are almost 10 years later, and still ongoing, and with many participants in the project, a growing community year to year, and that's going really well. And that happens only because how we design the project and how we structure the project. So we always looked at the project as a framework instead of a product. We try, basically, there is no, everything is done in a way to enable everyone to be welcoming to everyone. So basically, it serves as a flexible framework for building embedded systems of different use cases, different architecture, different ISAs, sometimes different cultures of how you do things in open source. The emphasis was always about enabling product development as well. So this thing was not just throwing some code out there and do whatever. We always wanted to go and enable product makers to take the next step, take Zephyr and do something with it. And that has been obviously, as many of you know, very successful. We have a lot of products based on Zephyr, and the community continues to grow, and we will continue maintaining this neutrality in the project and providing the needed infrastructure that equally enables developers and users to take Zephyr to the next step and do something useful out of it. Not that Zephyr itself is not useful on its own. You can still go and do a lot of useful things on any type of hardware. One thing that actually relates to what Kate was saying regarding the safety certification. Like one major problem that we always deal with when we're talking about safety and certification and what we want to do is, the question that always comes up is, hey, which hardware are we going to certify, or which microcontroller, or which architecture, and so on. And that's always tough, because Zephyr tries to address all use cases. I know it will be very difficult to certify and take Zephyr all the way to certification on all architectures with all features and so on. So we have to select certain aspects of the project and probably some use cases that are common for many of the users of Zephyr. So, the next step would be to take it to the next level with enhancing this and expanding the hardware support. But this is something, a tough objective and a tough problem that we always have to deal with. We have to be neutral, and we have to provide an entry point for everyone, and and not leave anybody at a disadvantage. So here, just to summarize, basically in terms of how we do things in open source and how things are developed. You have the upstream, in this case it's Zephyr, and we have many downstreams where people just take Zephyr, do whatever, they add their secret sauce, sometimes in the open, so that's not secret anymore, but you actually do your own things without having to go through the upstream processes and so on, and usually that's where a lot of innovations happen. Obviously, we welcome things to be upstream and be part of the project, and that happens usually. And that's really, one of the, it's enabling this in our infrastructure and the way we do things. For example, one thing that was introduced very early in the project was, how do I manage external modules? How do I integrate, for example, vendor hardware support HALs? How do I, add functionality that is not necessarily going to be at any time part of the project because of licensing constraints and so on. So this is something that we did like with supporting modules, with West and so on. And this is something that you can use build product on top of Zephyr without impacting the upstream development. And that's something we continue to support, we continue to encourage. And it's very important for everyone here to understand. And that's basically the main reason for this talk. I just want to reassure everyone here that Zephyr is open for everyone. And with the main message is that you are not limited to have everything in Zephyr. You can do your own thing with the long-term goal probably is to upstream some of these things into Zephyr. So the clear separation between upstream and downstream is something we encourage, something we try to follow, something we want to enforce. And that helps with getting more contributors, getting more companies, getting more vendors to actually participate and use Zephyr. It is usually very, very difficult to manage generic non-product related features when, for example, you don't have the end goal of knowing what certain features actually would end up in products. So that's why it's very important for us, at least in the upstream and the technical steering committee and the technical leadership in the project to understand, for example, why certain things are being added in a certain way in our project. So when somebody is submitting something and we have no visibility into where is that leading, what is your use case, it's very tough to get these things moving forward. So it's very important for any contribution and anybody submitting anything into Zephyr to at least have a hint and show that the problem they are trying to solve, even if it's targeting a product, is useful for other people other than them. Because if it's only useful for me, I mean, you don't have to upstream it at the end. You can just keep it in your downstream. So there are also a lot of downstream concerns that we always have to deal with and address. I mean, we can't just go and make changes that would break somebody's downstream. That goes to APIs, but it can also extend to testing, to test infrastructure, CI, and so on. So that's very important for us to always keep an eye on what's happening downstream, to allow us, things to run as smooth as possible all the time. I mean, we don't really make guarantees, like I can go and change our CI and without thinking too much about certain problems, and one day later somebody will come, hey, you broke my CI. I mean, that we try to negotiate and deal with these issues and improve as we go. But usually there is no a general promise that your downstream will always be functional. The expectation is that the downstream follows the upstream and try to coordinate with them as much as possible as well. So collaboration and communication, that's basically what I'm saying here. There's a lot of back and forth with the downstreams. Ideally, I mean, you want to participate. You don't just want to work behind closed doors and not exposing yourself to what's happening in the project. We have a lot of communication happening usually, and it is encouraged, for everyone to participate in making, using Zephyr downstream as smooth as possible in this case. So the conclusion here, Zephyr was started, continues to be a foundation for building products. We want to continue this. We want to keep it as neutral as possible. And we want to keep clear separation between downstream and upstream, encourage parallel development as much as possible so that you don't develop your product features on top of Zephyr and then fight for getting things into Zephyr to support a product which usually does not work. You always have to have your backup plan and run things in parallel. Otherwise, you will have problems with your management in this case. Yeah? And that's just to clarify, I mean, this is something we do at Intel. I know many other vendors do that as well using Zephyr, and it seems to be working really well. That's it. Thank you very much, everyone, and yeah, I hope you enjoy the show.
Thank you, Anas.
Thank you.
I'd like to introduce our next speaker. His name is Dan Mihai Dimitriou, and he's the CTO of Midakura. And he's here to talk to us about how WebAssembly can be used to make customizable devices. So please join me in welcoming Dan. Thank you.
Hi, good morning, or early afternoon. So I'd like to tell you a little story of how I came to be here, because normally this is not the kind of event I would be at. I'm much more not an IoT or embedded systems guy, more of an infrastructure and data center guy. So I'm working currently for Midakura, which is a subsidiary of Sony Semiconductor Solutions. And in particular, there's this new business unit that is focused on making smart sensors, using the portfolio of CMOS sensors that Sony has. So the whole idea is to build devices, to bring to market easy-to-use sensing devices that are programmable, that have a very low barrier of entry for solution developers, and that preserve privacy by not sending data off of the edge, and eventually make it easy to develop and operate, and cheap to operate applications that do sensing. So we can give some examples, but for example, you can imagine in the logistics space, things like tracking the container ID, for containers coming in and out of a port, stuff like that. So some of the challenges of embedded development that all of you know far better than me. And when we say embedded, typically we mean some application running on top of a real-time OS on a microcontroller, MCU. So it's not Linux, although I know there is such a thing as embedded Linux, but that's not mostly what we're talking about. So one, it's difficult. You pretty much have to code everything in C. Maybe that's not 100% true today, but that's mostly true, especially if you want to do real-time workloads like ours. After deploying, it's not so easy to change the functionality. You've got packed up your firmware, deployed it, and then if the device is not connected, then you're pretty much stuck. There's no standard component model, so there's customization cost is high. Typically, the portability isn't quite there because maybe some real-time OSs are POSIX compliant, sort of, maybe others are not. And then a lot of our problem is actually in the safety and security space. So memory isolation is not there because the MCU doesn't have a real MMU, like your x86 processor. And the real-time OSs are not really designed for multi-user, so even if they're like POSIX compliant, the syscalls are not checked in the same way necessarily, right? So everybody here knows very well. So I found this on somewhere in that the number one source of security vulnerabilities is memory bugs, and these are exactly one class of bugs that's affecting us quite a bit in this space. The other point I wanted to make is why do we need to care about polyglot development, like with multiple languages, especially for AI? Well, one thing to keep in mind here is that the most popular languages are like Python, JavaScript, etc. Not so much C and Rust. We all love Rust, but it is not that popular, generally speaking. And in particular, among AI developers, the language that's most popular is Python, and the frameworks that they use mostly are also Python-based frameworks, so we really need to care about that as well. So some of our goals are to ensure safety while enabling dynamic deployment of applications on these microcontrollers, these MMU-less devices, reducing the developer effort by supporting higher level languages, and component reuse, and generally speaking, enabling a more flexible QA process than we typically have in this kind of environment, because you don't need to QA the entire stack up to the same level if you have some isolation. And of course, portability across hardware platforms. So we developed this thing called EVP, Edge Virtualization Platform. Now, I'd love to tell you that it's open source, but unfortunately, it's not true yet. So hopefully, in the near future, it will be. We're working on that. So what is it? It's like Kubernetes, but for very tiny IoT devices. It does the lifecycle management of these workloads that run on these devices. The EVP agent is kind of like the kubelet, and, you know, drum roll, it leverages WebAssembly, in particular WebAssembly micro runtime, to provide the isolation of the software modules. So it can be secure even on a real-time OS on top of an MCU. Roughly speaking, it looks like this: you know, hardware OS, native libraries, hardware abstraction layer, and then the different modules that implement various functions running on top of the WebAssembly micro runtime, with a bunch of interfaces, native host interfaces that we developed. So this is kind of application specific to our domain, which is, like I said, sensing, but we have like a sensor interface where you can configure things like the frame rate or other, you know, ISP settings, communication interfaces, various communication interfaces. WASI-NN is like the standardized extension for doing neural network inference, and some sort of storage functions. So these are like, you know, of course, none of these are fully standardized except WASI-NN, but this is in our SDK. And more or less, this is what the developer wants to do with our setup. So the little white device on the right that you see is actually a product. You can buy it online, and it has inside, you know, a sensor, a DSP, and an MCU. You know, it's all packaged together, and you can program this thing with your neural network model that does the computer vision, as well as your application code, you know, to run something on the edge. So the developer can do this all locally using a CLI and an integration with the IDE. Okay, so, and we've also done this kind of like visual programming thing. If you have a set of pre-built modules, you can connect them together. This is a Node-RED interface, which you may be familiar with. We just kind of hacked up the GUI to be able to, you know, string together our application from pre-built nodes. It was just a demo, but you can see it at our booth if you come by. And just one example I wanted to give you is this license plate reading app. Happens to be Japanese license plate since we're from Japan. And so the idea here is that the developer was able to use and reuse these computer vision models that does the detection first of the license plate, then it does some other processing like cropping, scaling, and so on, and then another detection of the individual characters. Finally, a kind of application logic that creates a string essentially out of those detections, and that's the output from the device. So the image never actually leaves the device. And I'll be happy to show you the demo at our booth as well as another demo. That's it. Thank you very much.
Thanks very much, Dan. So I'd like to introduce our next speaker, and his name is Artem Arginsky. And Artem is the general manager of ARM-based processors at Texas Instruments. And he'll be talking about Texas Instruments' vision for transforming the industry through a proactive model of upstream software development. So we all love upstream software development. So please welcome Artem.
Thank you.
Thank you.
Hi, everybody. As mentioned, I'm Artem Arginsky. I put a picture of myself up there in case you want to see me at my wedding. Actually, I'm just very proud. But if you're trying to find me later to ask questions, remember who I am. But I am actually really privileged to be up here. My team has volunteered me to come up and talk a little bit about the journey that TI has been on, engaging upstream and really bringing the benefit of that to the embedded space, right? And I think the timing of how we made these presentations is actually great. You heard about the microcontroller embedded. You're about to hear about the Linux microprocessor embedding. So hopefully that happened on purpose, but maybe not. But anyway, as we jump into this, right, the reason why upstreaming is so important to us, that's the question that we're going to kind of take a look at. And I preface that because I think if I ask that question to everybody here in the room, there'll be a million answers and they're all correct, right? And it is very important. But why does it matter to an embedded vendor, a for-profit embedded vendor like Texas Instruments, right? And at the end of the day, it translates to, because it matters to our customers. Embedded silicon development is complicated. It's resource constrained, meaning nobody is happy with the device they get. Either it doesn't have enough performance, the power's too high, not enough IOs. Pick your use case, but there will be a reason your resources are not enough, right? So with that comes a lot of code optimization, right? Your application, your differentiation is still what it is, and you have to extract that out of the SoC, right? And then with embedded silicon, longevity is the king, right? It's the name of the game, so to speak. But why? Well, the cost of building an integrated system, a car, a train, an airplane, right, is very high. And you want to extract as much longevity out of that. So all of the innovation over time happens through software, right? So at the end of the day, our customers and the developers that engage with us end up being exceptionally restricted in what they can do unless we open source what we do, unless we give them back the software, right, and let them take control of that. And the only scalable way of doing that is through upstreaming, right? And I'll show you a little bit, but along the way, you know, TI had ebbs and flows of upstreaming, right? And we paid the penalty of that along the way. So pains learned, you know, fighting on the battlefield, so to speak. So what does that mean for us, right, at the end of the day? The upstreaming enables us to provide to our developers, and at the end of the day, to our customers and their customers, scalability, software quality, and longevity, right? And what I mean by scalability is very simple, right? It's exactly what I talked about, that customers have to optimize their software. They have to do something different. They can't simply take my code-locked SDK, right, and be able to innovate, right? And software quality, right? If they're going to take control of that code, they have to be able to trust that that code was developed well, right? And if you're developing a closed source system, it's very easy to dilute yourself into thinking you can take a shortcut here, maybe a shortcut there, and before you know it, a lot of shortcuts added up to bad software quality, right? By the nature of upstreaming open source, you have to get that validation across the community. You get the brains and the innovations and the collaborations across the industry to really figure out what is the best solution, what is the right answer, and how do we attack. And at the end of the day, that translates to longevity of the silicon, of the code, and the end system that our customers use. So I'd like to preach that, of course, but at the end of the day, how did we arrive at that, right? It's not rocket science. I know all of you are sitting back thinking we figured that out 20 years ago. What's taking you so long? Well, that's what's taken us so long. It's pains of growing, right? If we look back 20 years ago, TI in our OMAP days and the cell phone days decided to expand beyond cell phones, right? Let's go attack other applications. Let's open up our code base. And we started engaging the Linux community back around 2003, upstreaming some drivers, really engaged in our SoCs. And along, you know, the next 10 years or so, we made a lot of strides, all the way up to joining the Yocto project and moving all of our SDKs into Yocto. But after that, we kind of moved into, okay, great, now we have thousands of developers on our platforms. It's exciting. We're starting to make some good money in the industry. Our silicon is selling, right? What do we do next? Well, we sort of maintained that direction, right? We kept releasing more SoCs, but we didn't really invest more into upstream. We did just enough to bring the kernel up to speed on our devices, maintain it, release LTS, but not engage the broader ecosystem, right? And then about 5 years ago, we released our new platform, the AIM6 platform, that at the end of the day kind of enabled us to go broader. So now we have to deal with 10,000s of developers. That's a lot of developers to satisfy. And what we quickly realized is we have to take up our investment on upstreaming, right? And when I look at my team, I only give them 2 metrics. And please meet Qasim, he runs my software team, and you can hear it from him directly. But I only keep 2 metrics for my team: high quality software and 100% upstream. That's the only way we can scale, and the only way my customers can scale, right? But of course, open source software isn't enough, right? You need open source hardware, right? You need open source tools. You need documentation. You need all of these components to come together, right? And it's really important to release that information out to the world, right? And I always urge ourselves and our partners, think open first. It'll improve the quality of everything you do, right? And at the end of the day, you won't lose a competitive advantage, because the competitive advantage is actually the customer experience. Our customers select us because they want to, one, minimize their investment. The less money they spend to build a product, the better, right? But at the end of the day, if their software engineers hate us, you'll never actually get to build a product with them, right? So it's somewhat self-fulfilling, but that's the way it should be. It's a win-win situation for the community, for the ecosystem, and the embedded vendors. All right, there we go. So what's next, right? How do we go from here? We upped our investment. We're interested in upstream. You see us in all the mailing lists. We're engaged. We welcome you to engage with us. But where do we want to go next? Well, what we want to do is dispel what some end customers may consider shortfalls of upstream. And what I mean by that is often you hear customers say, I have to go out of the tree to do safety, right? Sometimes they'll say, I have to go out of the tree because I don't get enough performance. I don't get the latency I want. I'm going to go build my own SDK, my own OS. I'll use some custom RTOS from the world, right? And those are just simply not true statements, right? What it means is we collectively as the industry have to go invest in these innovations to go bring safety to automotive, as you heard earlier today, to bring KPIs that automotive customers care about, like fast boot, right? Your laptop waking up in 5 seconds or 6 seconds doesn't ultimately matter. Your car turning on in a second or 10 seconds matters a lot. Why? Because your backup camera has to turn on, because maybe you already shifted the gear and the car started backing up. You don't have 5 seconds. You have 500 milliseconds, right? Half a second. So all of those things matter, and they matter for us to make that investment in the upstream, in the main line, because it's the only way collectively we're going to be able to scale, right? And then, of course, standardizing tools and performance metrics, right? Collaborating together to really have a bar of measurement, right, that we can all really satisfy what is success for us at the end of the day. But as we get on this journey, what I'm most humble is by my team that has taken me through this journey. I learned Linux along the way. I've been here for about 5 years running this business, and I've learned a lot from my team. And I'm actually really hoping that you guys come by some of the presentations we're doing today and learn from them as well. But I look forward to hearing from you. Come by our booth and ask me any questions. And more importantly, tell me where you'd like to collaborate with us. Thank you.
Thank you very much, Artem. Much appreciated. Certainly agree with that. So now our last speaker is our esteemed co-host, Tim Bird, who is a principal software engineer at Sony Electronics. And Zephyr's been learning a lot from embedded Linux over the years. He's been definitely a model for me. And so Tim, recent year, one of the last recent ones, shared his experiences down to Antarctica at a recent LC. And I sort of took inspiration from this. And so we wanted to make sure we had some Zephyr presence down there. So we have Zephyr's flags there. They wouldn't let me fly it down there. Otherwise, I would have tried to get it flying because of the bird flu that's happening right now down there. And so the only thing that can touch the ground in Antarctica right now is your boots. And there's a really strict protocol. But we do have a Zephyr down in there. And if anyone out in the community has a Zephyr kite at one of the bases or something like that and flies it, please post a picture. And I also lack his penguin suit, so oh well. Anyhow, Tim's here to talk about the challenges of overcoming embedded open source software development, which is something we all care about. Thanks, Tim.
Thanks, Kate. That's an awesome picture. If you ever have a chance to go to Antarctica, it's like no other place. Really interesting. So, in the last year or so, I have spent some time actually in the space sector doing some research on space issues, particularly open source software in space. You may not realize this, but Sony was actually involved with a project that landed on the moon in February, and we have some other space-related projects, so that's something most people don't know about Sony. The very first thing I learned, and actually I think everybody knows this, is that space is hard. And you can see that by the number of things that don't quite work out as planned. Even on the mission that we were on, which we were on a little rover that was on the SLIM mission by JAXA, we had problems. The SLIM lander didn't land in optimal configuration. And The thing that really has struck me about the space industry is there are so many constraints. You know, we're used to having constraints in embedded, but man, the space sector is, you've got temperature issues, you have radiation, you have to be able to run in a vacuum, vibration. That's just the hardware stuff. There are limits on power. If you're trying to go out on a 1U CubeSat, you know, you're lucky if you can get a half watt out of the solar arrays on this little 10 centimeter cube thing. Requirements for performance, fault tolerance, real-time power management, and there's an extremely high cost per mission. A lot of times the missions have one unit. I'm used to consumer electronics at Sony where we're shipping hundreds of millions of units or something. You can amortize costs. You can't do that in space. And so there's just, because of launch costs and operations costs, a mission is very, very expensive. And so you have this failure is not an option. And that actually creates a cycle where you do additional testing. You over-engineer for robustness. That's why some of the landers, the rovers that go up on Mars, you see they last like 10 times their expected lifetime because they've been over-engineered. And the thing also about space that's interesting is that everything is new up there. They're still doing fundamental science about space. And a lot of the missions, and the focus is on the payload. I went to a conference, I tried to get people to talk to me about the operating system they were using. Nobody could talk, well they could, but they're talking about the payload. They're always talking about the payload. And almost every payload is bespoke custom hardware. And even the base systems are using novel hardware, so the thrusters, the batteries, the stabilizers. And the missions are trying something new. Everyone wants to try and learn new things. And so there are exceptions, however. So we are starting to see COTS hardware applied in space. So SpaceX famously is using x86 COTS processors on their rockets. And the way they're doing that is with triple redundant pairs of x86 processors to handle the fault tolerance. And there's Starlink, and there's a company called Planet Labs. They have satellite constellations, 2 of the largest constellations up there. And they're using x86 processors. They're not rad hardened, which is really interesting. And they can do that using algorithmic redundancy. Most famously, probably the Mars Ingenuity helicopter and the Perseverance rover and back shell used some off-the-shelf parts. They had a Qualcomm processor, which is a mobile phone processor. They used COTS processors. They actually used sensors that they got from SparkFun, which is pretty cool. So why am I even talking about this? When I got into space, it was nostalgic for me. Way back early in my career, I used to do hand-coded assembly for embedded projects. And it just reminded me of the issues that we all face, the issues of constraints that we're dealing with, and the fact that we often have custom-purpose devices and software. And it's often hard to find people to talk to about those things, particularly for some parts of the stack. And so a lot of times, let me talk about how that interferes with, that creates challenges for doing open source. So open source means collaboration. Please forgive me for doing a little bit of a remedial back step here. This is resembles some of the training I do at Sony for some of our new engineers. So open source is defined by the ability to use, but also to contribute to the code base. So it's not the same thing as source available. And in my opinion, there are 2 really key effects, the many minds effect and the problem solver effect. And those are terms that I've come up to. So what is the many minds effect? We've all heard this before. It's that the variety of experiences and skills results in better ideas. And so in open source, we're trying to achieve a meritocracy where the best ideas win. And I like to use a light bulb analogy. So ideas for a project are like light bulbs. If you have a small community, then you'll have a small number of ideas. And just mathematically, it's really, really interesting. If you have a large community, you're going to have more ideas, more people contributing to it. And that just gives you, mathematically, a better probability that you're going to have some really good ideas in there. Okay, so in when we expressed in terms of bug fixes or bugs, the many minds effects is often referred to, this is referred to as Linus's law, which was actually coined by Eric Raymond. Given enough eyeballs, all bugs are shallow. And I prefer to break that into two parts because I never kind of understood that line by itself. But basically, with the right eyeballs, you can fix any bug. But you have to have enough eyeballs, right? With enough eyeballs, you have a better probability that you'll find the right eyeballs that'll see your bugs. And notice, this was key to finding the XZ backdoor that we just had. I don't know if you've read about the XZ backdoor, but it was a developer not involved in compression who found that, right? So the fact that it was open source allowed people to find that and fix that and mitigate it before it got out into the wild, which was really, really important. The other key effect of open source I call the problem solver effect. And so what that is this is a little picture of an amoeba. Problems are solved as they are encountered. So the software has to kind of come in contact with the problem space in order to advance. So most software is written to solve a specific problem. In fact, I think it's 80% of all software is just in-house software that's written for a single task. It never grows outside of its original niche. So, but open source is different. Open source software can grow outside of its original niche because people use it for things that the original author never intended. And this results, and I see this in my own projects. I have this little project called Grab Serial on GitHub, and I used it for timing the boot up time of the kernel, right? Because I used to do a lot of work on boot up time reduction. And, but it turns out, and I put it on GitHub, it turns out that all of the features that have come into that product in the last 10 years have been from people who are using it for other things. It turns out that apparently people use it to monitor data streams on serial ports. So it's weird because as the maintainer, I didn't originate probably, well, like maybe 10% of the features in the last 10 years are features that I originated. And that's the problem solver effect. As people use software for an area outside its original scope, it grows and it becomes better. And then this results in the EOSS virtuous cycle. The more problems a piece of software solves, the more users it attracts, and the bigger the community gets. Well, how does that interact with this problem from the space industry? And just really quickly, I want to talk about generalization versus specialization. So we all know the difference between Legos, and these are the parts for a model spaceship, right? So if you're going to build a spaceship, arguably, it's much better to use the parts from the spaceship kit, right? You're going to end up with a better spaceship. You have these custom pieces that are exactly fit for what you need. Now, you can make a spaceship with Legos. There's a picture of one there on the right. But the difference is that with the Lego pieces, you can also make other things, right? You can make a boat or a car or a house. And even though the spaceship pieces are better for making the spaceship, the custom pieces, the Lego pieces are more general and they're more versatile. They can be used by more people. And you see the exact same effect on using modern hardware. So a modern processor has all kinds of stuff on it that you probably won't end up using on your project, right? And the reason for that is the processor vendors are giving you a bunch of features that you can customize. And so a lot of the act of doing embedded work is specializing, trying to use just the portions of the OS stack, the user space stack, and the features of the processor just to optimize it, much as Artem was talking about. And so you can think of the parts of the processor, the parts of the software stack that you're not using, kind of like the extra nubs or the rough edges on a Lego model. The other thing that happens because of this customization, this specialization, is fragmentation, right? The most famous fragmentation was arguably the Unix fragmentation, when Unix fragmented into a bunch of different camps because people wanted to specialize. The vendors wanted their own secret sauce for their customers. But those different APIs meant that it was difficult to create an application ecosystem. And so the Unix fragmentation, I'll remind everyone, led us to auto tools, which of course led us to the XV backdoor, right? And so this fragmentation is not good. It adds complexity. And a divided community in particular reduces all these open source effects that are good for our industry and good for our ecosystem. So given that we have these problems with embedded people always trying to specialize and open source people always trying to generalize, well, how does Linux make any inroads at all? Well, of course, we all know that. We wouldn't be here if we didn't recognize some of these benefits, right? That if you get into open source, the chance that there's something already there that you need that's already written will be there. That's really high. If you look at what's available in Linux compared to RTOSes in terms of the tools, the drivers, the libraries, you can share the development cost even with your competitors. And there's a vast array of open source software available on Linux. Sometimes isn't even available on things like AI and ML. So we have the availability of this stuff. And that extra software sometimes comes in pretty handy, even on a space mission where you'd think everything was predetermined. But it turns out several of the space missions that I researched ended up using shell scripts and Linux distro features to resolve issues when they hadn't intended to, right? Sometimes these issues come up. Ingenuity famously ended up using compression to solve a log archiving problem and a data management problem. That was not in the original plan, but hey, gzip was on the distro, right? It was one of these extra things that they had not planned to use, but was there. And the same thing happened with Asteria and Alto CubeSats. I won't go into the detail of the stories there, but having those extra features, even if you don't plan to use them right now, is really beneficial and can be for your product. Even if your product is hundreds of millions of miles away and you need to do something you didn't anticipate. So given these challenges, what are some of my recommendations to overcome this dichotomy between generalization and specialization? And I have it down to just these 4 things. So very first thing, you want to increase the community, right? The bigger the community, the more open source effect you get. So the very first thing, step number 1, join a community. If you're not on the mailing list, if you're not in the project as a visible member of the project, then the community is less one person than it should have. And then you should enhance the community, right? You can invite others. Do something to make the community more valuable. A lot of us are hesitant to join communities because we don't think we have something to offer, right? A lot of people get it totally backwards. They think that the first thing you got to do is commit code. There are so many other ways to add to a community. And actually, I think the very first thing to do when you join a community is talk about your usage of Linux. The maintainer can't take into account your requirements if he doesn't know them. And so when you get on a mailing list, just say, hey, guess what? Especially if you're doing something different, tell other people about what you're doing, how you're using the software that's different from how they're using the software. That is so valuable. I'm a maintainer for a couple of projects myself, and I love to see new users and new usage reports. And there's all these other things you can do. The other thing is make sure that you improve the generalization. This means that you have to when you're making contributions, you have to take into account what other people's use cases, what they want to do with the software. It's so common in open source for developers to fix their issue, and that's good. That introduces, that helps the code base grow into a new niche, but you have to take into account other people's use cases. The more you do that, the more that the open source effects kick in. The other thing, don't specialize where you don't need to. We're seeing this actually in the space sector. I already talked about it a little bit. Use the same hardware that others are using, right? Don't go off on creating weird stuff if you don't need to. Use the same subsystems. And don't over-reduce. There's a temptation in embedded. We now have the luxury. Our processors are advanced enough. We have a lot of memory on modern embedded systems. Zephyr can tackle the low-end stuff. With a Linux system, you're usually talking 32 at least megabytes of memory. You don't have to trim down every last little thing. So leave some stuff in there just in case you want to use it later. And then the last thing, and this may be the most important, is find allies that care about your issues and work with them, right? So if you care about small system size, of course, if you're doing IoT devices, you care about that. Well, it turns out that the security researchers also care about system size because they want to reduce the attack surface. So they have something in common they can work on together, they can collaborate on. With Quick Boot, right, we've heard about our automotive Linux and consumer electronics, right? But it turns out desktop users also want fast boot. And cloud servers also want fast boot. So there are other people in the community. Don't make the mistake of thinking you're the only person in the community that wants a particular feature. And then low power usage, right? We all know that mobile phone and IoT wants low power usage for longevity of device. But turns out the data center people, right, who are using a significant portion of worldwide power, they also care about power. So find your allies in the open source world and work with them. And if you do that, if you overcome some of these challenges, one, it's possible to do it. You can make the world a better place, not just for yourself, but for others. And the great thing about open source is while you're making the world a better place for everyone, you're also making your own development life easier by working upstream. And so with that, I will say thank you for your time.
Thank you, Tim. You may as well hang up here with us. Okay. Anyhow, it's now time for lunch, everyone. And so if you are attending the women's lunch, it is in the terrace suite 2 on level 4, so 1 level down. And if you are not doing that one, there's a lunch now in the Solutions Showcase on ballroom 1 here on level 5. And again, thank you very much to all our speakers, and thank you to every one of you for coming here and participating in this event, and we look forward to working with you. If you've got any questions, I guess the information desk and registration folks will help you.
Okay, thanks.
Thank
Let's
you.
go have lunch.
Lunch.
With a cigarette, I picked myself up, fixed my hair, and I said I'm gonna go talk to her.
So hello everyone. I'll start my presentation. So I'm Cédric Lescope. I'm working for Schneider Electric. Schneider Electric is a big industrial company, so we have a different line of business. This means that we are producing lots of different products, so I won't talk about all of them. I'm working on the drives lab, so it means we drive motors to build other products like leverage or pumps control or stuff like that. And back in the days, there was no need about communications, but today there is a lot of communication needs about field buses, like can open Ethernet IP, backnet IP, DeviceNet, and stuff like that. So we added to our product some option board, so we call that communication board to implement the field buses. And going there to say that I'm a firmware architect on this communication board. I'm also working on projects that we call innovation project. So we are looking at different OSs, RTOS. So I'm really interested about Zephyr, so that's why I'm here today. And I will introduce you with a new feature in Zephyr, which is called LLEXT. So today I will introduce, I will tell you a little story about me and about my project. And it all started with an industrial need, a need about flexibility, because as for today, I think like maybe almost all firmware, not all, but most of the firmware are monolithic. That means we have to flash the whole firmware, and when you want to update it, you have to reflash everything. And our new needs was to be able to amend a firmware without reflashing everything. So that's what we call flexibility. So why do you want that? Because as an industrial, the time to market is very important. So doing that, it will mean that you don't need to do a verification about the whole firmware, to redo the whole validation, and maybe not the certification. So that's what we want to try to do, like having the base firmware on one side, that we do the verification once only, and then have the application on the other side, and redo only the verification if there is a problem on it. And that's it. So, pretty much it. So, just to give you a quick view about the image, what we want to do is that we have the product in the middle. So here is a soft starter, an ATS 490, which used to have a monolithic firmware. So now we want to replace it with Zephyr. Today there is no, it's not yet done, but it's kind of my dream. On top of that, we can see that there is a proprietary infrastructure and the motor control. And what we want to do is like to add an application on top of it, maybe 2 applications. And by application, I mean anything. It's not only something that we can find about Zephyr sample test. It could be like something under modules. So as a communication architect, I'm looking at adding a new communication stack to the product without refreshing it. So what we have done, so as all companies, we have done the state of the art. So we were looking at what was already existing on the market. So the main idea was first, as all industrial, to do it ourselves. So to do it the proprietary way. So that is really great in the first place because you can do it yourself. So you can implement everything as you want. But the counterpart is the backdraw is like as any proprietary code, you have to when you want to modify it, you have to reread it. If you hire someone new, he has to ramp up on it, and you have to understand it the proprietary way. Just a quick story about that. Last week we had an engineer who retired, so it was working in Schneider Electric for 25 years. And when he started to write the first line of code for our product, it was written in assembly code. So today if someone new is hired, he has to read some assembly code. So it's not really great. So we would like to move on something more open source. So maybe someone new that we hire will know the technology, and the ramp up will be less significant. So then we started to look at other technology, and we found out that ThreadX, maybe you know this RTOS, it was first from Microsoft. And in ThreadX, they are implementing what they call modules. So modules is doing exactly the same as LLEXT. It means we can add a new module to a product on top of ThreadX, and this is working fine. We didn't pick this technology because in other LOB, we had some bad feedback, and a few weeks later, we saw that Microsoft was moving ThreadX to the Eclipse Foundation, so we said, okay, maybe they are dropping the project, maybe we won't go there. Then we look at other technologies, like, well, I won't say the name, but it was based on the Java machine technology. So it means that you could write any modules on top of this Java machine. So it was really nice because everything was sandboxed. And, but for us, it was a big drawback because it meant that we had to rewrite all our products, all our firmware from C and assembly language to Java language, and we didn't want to do that, too much time consuming. So we looked at Zephyr, and we found out that it was a few months, many months ago now, so last year, this new feature was, this new subsystem LLEXT was rising, so we had a look at it, and it was very promising from what we wanted. So what does LLEXT? What it does is very simple. It's taking a ELF file, so I think everyone knows the ELF format. It's like an open source format. You can, it's like it's cut in different pieces. You have a header that says that you have different sections, and in this section you have the text section for the code, and you have the data section for the data, or the BSS and unit, etc. So what does the LLEXT? First, it parses the whole ELF, and it is looking for the different instructions about which are about the relocation. So first you have to look at you have to find the instructions, so different moves, jumps, and thumb arm instruction, and you look at this instruction, you decode them, and then you relocate them onto RAM memory to be able to execute the code. So when we started there was only one backend. It was the serial lines. So someone who wanted to use LLEXT had to build an F file and send it on the target via the serial lines to get it parsed, to get it onto the RAM, and then execute it. It was coming with a very simple example, which was doing one print K to say hello world. But it was very nice because hello world was implemented in the base firmware, so it proved that an extension could call some code from the base firmware. The only problem at that time is that when we took the project, it was at a POC state, so it was not very stable. It was very unstable because if we tried to do 2 print Ks, it crashed. So that's how we started with LLEXT. So what we had to do is what I call enhancement. So what's kind of adding what was missing. So there is not so much missing. We added the ARM instructions that were missing. So I think it was only the thumb extension that move and jumps. We also added a mechanism to export and find symbols. What does it mean? What it means is like when you have the 2 firmware, so the base firmware and the extension, they all have symbols, and they need to communicate to each other. So the base firmware has to find symbols onto the extension, so that we implement some function to say, okay, look for some hard-coded symbols, so init, start, stop, exit. And the other way around, the extension has to know where are the other symbol from the base firmware. So if the extension wants to create a thread, for example, it has to know where the thread function is. So we had this mechanism. What was also nice for us that you cannot find it yet in Zephyr, but maybe soon. It was a way to build the extension health, because when you build the new health, your extension, you have to use the same, let's say the same GCC option and the peak option to say, okay, I want to build the extension with the same mechanism. So we edited the CMake files and the kconfig, etc. to make it work. And I think today, if you look at the code in Zephyr, it's not the same approach they use. I think someone pushed a way to build the extension out of the tree. So there is like a small SDK to build extension. Maybe we'll have to talk with them to say, okay, maybe we can have the two mechanisms. Anyway, we try to propose our way to build the extension from the tree. It's a bit like in Linux. In Linux, when you start kconfig, you will see like your driver, your modus, and you can tip the driver, and it will be built in. And you can say it will be a module, so it will not be built in the kernel. It will be built just next to it, and then you can load it. It's the same mechanism. We try to mimic it. And the last thing we were needed was to install some kernel callbacks because of the mechanism of Zephyr. Zephyr, if you want to be attached to an IRQ, or if you want to be attached to a GPIO, you have to use a callback. So we implemented a way for the extension to be able to install a callback inside the kernel, so you can get noticed if there is an IRQ or if there is a GPIO. I will show that a bit later on. How? We also had some modifications, so we add a new backend because we didn't want to have the target plugged to the host computer to send the ELF files through the serial lines all the time. We wanted to be able to put the ELF files onto the file system and then ask the target to automatically load it at the start. And to do that, we also add a configuration file. So it's a very simple. It was a very simple syntax. I think we took the ini syntax. Maybe you know it. It's just a few lines where you say I have one ELF file which is located on the file system at that path, and then the LLAC finds this file, reads it, and so okay, you have like many ELF files, and the loads automatically them onto the memory and then run them. We also fixed a few issues. It was not very big deal to be able to do many print case, not only one. And then we also proved that we could call any function from the kernel. It was not only print case, but it could be any function that we export. So create a thread, create a mutex, create a semaphore. When you create a mutex or semaphore, you have to take care about a few things like permissions, because in Zephyr you have to add permissions to do stuff like that. So we have to keep in mind that. So to prove that everything was working, I will show you a proof of concept that we wanted to do. So on the picture, you can see a counter plugin. So yeah, because when we started to implement our own mechanism, we didn't call them extensions, we called them plugins. So I didn't re-edit the picture. So when you read plugins, it means extension. So what we did is to create two extensions. Was a very simple extension that we call counter. Basically, it was it's counting the number of frames that a master. I will do a quick summary. We plug the target was configured to be a slave on the CanOpen stack. We use our host computer to be the master on the CanOpen stack. And the CanOpen stack on the target itself is supposed to be an extension. So we took the code in Zephyr. If you look at modules, which is an external module, you can find the CanOpen node, which is open source. And we, instead of make it built-in inside the firmware, we built it as an extension. And we wrote a really simple other extension, which was a counter which is counting every frame that which is incrementing a counter each time a can frame is received. And we plug see the picture, the small blue button, just to prove that if we press the button, we can have a callback on the GPIO and reset the counter. So with all of that, you can prove that first you have a product which don't have the CanOpen stack, So there is no communication possible with the host on the CAN bus. You then load the two extensions. So your product is now having the CAN open stack on it. So it was it's really a runtime amend. And then you can communicate with your host through the CAN bus. In order to do that, we use the STM32 Nucleo board. So it's an innovation board based on ARM Cortex-M4. We installed two extensions of the file system, and with the configuration file to say, okay, we want to load them. And we also had to do some work with the MPU, because at first the MPU was not supported. Today it is supported, but there is some conversation we have to with the community to be sure that what we do with the MPU is still in the community philosophy. We don't want to, well, we will do a proposal. After that, we went a bit further, that we tried to experiment the XZIP, because from now, when you do the ELF is loaded into the RAM, but we wanted to know if it will be able to flash it on the ROM and be able to execute it on the ROM. We also look at the Zephyr user space. So here we had some kind of issue with the MPU, because there is not we don't have the same philosophy that the Zephyr community on the MPU, so we have to open a conversation about that. And we did some performance measurement to be sure that even if a code is running as an extension, or if it's running as built-in, there is no impact on the performance as real-time or stuff like that. I will show the demonstration afterwards, but here we have a quick view about what's happening at the very, I don't know if you can see. Let's say we can see it. It's just written loading plugins. So we are here, Zephyr is starting, and it says I'm loading the plugin counter, and I'm loading the plugin CAN open stack, and it's running then. I will try to show you with I brought my webcam, and I will do the demonstration at the end. You can read it? Well, it says loading plugins successfully loaded, and starting plugins. So you have the first steps. It's like first you take the extension, you load it, you say okay, it has been loaded fine, and then you start it, meaning you found the symbol in it inside the plugin, and you're able to call it. And we did that 2 times, one for counter and one for the CAN open stack. To do a performance analysis, we use the conventional tools. So I think many of you knows MATLAB Simulink. So Schneider is using Simulink to do some simulation. So we do model-based design. So we basically built a very simple model-based design. We injected some input vector, and we recorded some output vector to build curves. We did the same on the target. So we took the code from Simulink as a C file, so you can auto-generate it. And you compile this code as an extension, and you send it to the target, and then you inject the same input vector, and you record the same output vectors, and then you compare. So here is the comparison. So what is great is that you only see 2 curves, but in fact, if you look at the legend, you have 2 times 2 curves, because there is 2 blue curves and 2 pink red curves. You can see them because they are completely overlapped. It means the simulations in blue is giving the same result as the code running on top of Zephyr, meaning you can run the extension, you can run your code on the extension, and there is no impact on the real time at all, because here you have the exact same outputs giving the same input vector. So it's really great. It means you can use the extension in your product to do your know-how. And then we use the more sophisticated tools where you need to have some license. Zephyr is already supporting Percepio. So if you look at Zephyr source tree, you look for trace analyzer, which is Percepio tools, analyzer tools. And then I won't go into too many details here because it's not the purpose of the presentation. We had to check a lot of stuff like system. You can check the tags, the system calls, user events, CPU load, etc., etc., etc. And that's what we've done for some times. And we get to reassure that the extension is not changing the real time, the task scheduling, etc., etc. So what are the impacts of the products? There is some benefits and some drawback. So the first benefit is what we wanted. It means you can do some partial updates. You don't need to send your whole firmware through your network or your way to update the firmware. You can only send the extension. So you spare some space and sometimes on the networking. Maybe it can be it's not free to use the network to update your products. And you get some impact on about your verification. You get a lot of time because you can only verify the extension in your product, and so your time to market will be a lot smaller. The biggest issue that we can see with the LLEXT, I think a lot of you already thought about that, is the cybersecurity. What happens if someone is able to put an extension on your product? It means maybe he can take control of your product because you are executing some code that you don't know. So here we are, I'm not bringing any answer at all. I'm bringing some question to the Zephyr community. And I'll just say, how do we do it with being cyber secure without exposing our new product to threats? And is there a way, for example, when you use your bootloader, the first stage bootloader, second stage loader, then you see your secure application. Maybe we'll have to be able to build some secure extension, something like that. Or is it enough to simply make sure that the extension is coming from a source that you know, and maybe with I don't know with cybersecurity tools like some private key, secure key, etc., etc. So it's a question. We are bringing question here. Maybe I hope we have some questions, some answers. And the other question is about safety. If we actually build some extension of your product, do you have to, first of all, can you certify as a safety level a product which is using extension? Is it possible or is it not possible at all? And if it is possible, now if you update your product with an extension, do you have to do the certification again or not? Because maybe you are updating some part of your product that is not certified. Do you have to redo everything? Do you have to redo everything or not? So that's some question we'd like to have, some answer we have to have. Okay. Here is the last part of my story. Is what happened when you are in an industrial company and you want to share back your code, because the point is, so we use Zephyr. We took the LXT technology feature subsystem, and I wanted to be able to share it back because we improved it and we wanted to share it back, and I wanted to see if it's possible as an industrial. Because when you do that with open source, since you share with the world, it means you're also sharing with your competitors. So first you have to be sure that you won't get any impact on your products, on your sales, and you have to be sure that your whole company agrees with it. So first, what you have to do is what I have to do. It was to check that we had a process internally. Which is not the case at all. I don't know if in a different company you have already some processes to share some code about open source, but in Schneider it was not the case. But now today a process has been built, and it's not fully operational yet, but we are I'm really proud of that. So like we actually can share some code now. I will share something at the end about that. What we had to do was looking that we are not using any patterns, some internal patterns first. So as a big company, like you have to make sure you go to see your IP department if you have one. It's not always the case, but we do have some lawyers, so we have to check with them first if the code is not using some other pattern, maybe, or competitors' patterns, and that we have the right to share it with the community. And the last one, but not the least, you have to get an approval, which is a very complex things to do with a company. You have to get all the people you need. Okay. And had to also to check the process from internally with externally, because Zephyr project has a process which gives you the guidelines. If you go to the website, you will see some documents which say you have to do this, and like that. It's not really to make them both work together, because when you look at Zephyr, since it's a Git process, they are used to have some small commits to review, so it can go fast. But as a company, you will never propose small commits. You will have to do the whole stuff. So in my POC, I was giving the whole feature, and then when I wanted to push back to the community the whole feature, the first answer that I got was, "You're crazy. There's too much code to review. Can you please cut it in small pieces, because we have to understand what you do, and we have to be sure that it's secure and you don't do anything crazy." So that's what I had to do. And pros and cons, which is great with the Zephyr community, that we have a fast time reaction. There are many people, I was very surprised with that. I got answered like half a day. I got an answer and review about my code, and it was really ongoing. I was very impressed. And because there is a lot of eyes, so here it's a pros and a cons. Because since there is a lot of eyes, they review the code, they found some issues with my code, which I had to fix. But also, the drawback is that since you have a lot of eyes, it means you have to content everyone. You have to make sure that everyone is happy, because if someone is not happy, they say you will say no, you have to do the review and start again. Well, that's life in Git, but that's the way it is. So, but it's a great thing. So I just want to show you that something I'm proud of is like a few days ago I got my first pull request accept on the Zephyr community. So it proves that it is possible as an industrial to share back some code. So here there is not everything. It's already just a small piece of what I want to share about the feature, but it's already a success, and it means it's possible to share back. That's it. And I would like to, if I have time, yeah, I have a lot of time. I will show the demonstration. So it'll be very, very quick. So what you can see on the picture, and I will show you the rest of the demonstration. You have the ST board I was talking about. You can see the green board is a piece of our product. I didn't want to use the whole product, so I cut a piece of it to get the connectors. You can see the CAN module, which is basically transforming the signals to get the CAN of the campus, because the board is not doing it. And then on the CAN option board, I plugged an adapter, which is doing some CAN to USB, and the USB is plugged back to the host computer, and then you can have communication on the CAN bus from the host to the target. Let me try to show you. Okay, you have it for here. For here. This one is just next to me. So, okay. Top left hand side is communication, which will be the CAN communication from host to the target. Bottom left, it's console and the target. And on the right hand side is my Zephyr project, where I built Zephyr and the extension. I will just use it to show you that if I do just ls on /f, well, you can see it because maybe it's too small. But basically, just to show you that on the file system now, there is no extension at all, and there is no configuration file. So if I start it, if I start my board, reset. I need to open it first. Sorry. Cyber security. Up, up. So here is the serial line. If I start it, Okay, so here you can see that there is no CAN. The CAN interface is ready because the CAN physically is there. There is no CAN stack, and you can see that there is no configuration file. The plugin.txt is not found, so nothing is happening. And if I try, okay. If I try to start the Python, which is implementing the master on the CAN bus, it won't work. We have some errors because there is no CAN on the target, so there is no communication possible. So now, on the right, I'm comparing the extension file plus the configuration file on the target. So now if I restart it, it will be fast, but as I showed you a few minutes ago, you can see that now the two plugins are loaded and the CAN stack is started. So you can see starting plugging CAN open node. And you can see that it's printing that there is just to show that there is a loop on the CAN which is waiting. And starting the pattern now. So you can see that you can see a counter which is increasing, which means there is some frames that are exchanged between the target and the host, and it's incremented. And if I press the GPIO, like I showed you a few minutes ago, the counter, which is now 47, 48, will go back to 0. So 50.01, it means the extension, which was a CAN open stack with a small client, was able to communicate with the host and reset the counter according to the GPIO. So you can see that, how to explain, there is a communication with everything. So that's pretty much it. That's it. That's it for today. Thank you. So if you have any questions.
Thanks. Hey, how's it going? That was a great demo. Just curious if you guys were able to debug your LLX as well, and if you could maybe just talk about that process.
You can debug it as any application, except that when you are using GCC on GDB, you have to load the symbols of your extension because the addresses are completely wrong. Because when you load the elf, the addresses are wrong, and they are partially updated with the LXT when they are loaded. So if you add the address to GCC with GDB, really simple, you can debug it as any application. It's not possible with IAR.
Okay, thanks for your presentation and for the contributions. I have a question on how are you going to handle in the company the long merging process? Like if now it takes a long time to complete the merge, how are you planning on supporting this internally? Like, are some products being developed now? Are you going to use your own version internally and then update? Is this something that...
That's a secret. I cannot say today that we are using Zephyr. So no, we are not using Zephyr, but yes, I will do the maintenance of the code to make sure that the community have the whole feature, if possible. And maybe sometimes we will use Zephyr, but I cannot say that today. It's not something I can say.
Have you done any measurements on like the overhead of having to store this ELF file as opposed to just having it in your application to start with in terms of ROM space or RAM space?
Yeah, we've done lots of. I didn't put it there because it depends on the target. But yeah, we do some measurement about the ROM. So on the file system, you have the space you have to use. Then it is the same on the flash. And also, what was really important, it was the time to actually load the application, which is, I think, the very, let's say, the bad key here, because it takes a lot of time to parse, because you have to take the whole text section, and you have to parse it entirely to put it on the RAM, because you have to find the instruction to be able to edit them. And this is taking for the small extension counter, and my board, it took 10 milliseconds to load it. So it's for a very long time, lots of time. And I think it was, if I check here, that we don't. Here you cannot see it, but here it took 160 milliseconds to load the can open node stack and on the Cortex M4. So it's a lot of time. I think it was your question? More or less. Sorry.
Okay.
So, is it possible to modify the existing running kernel functionality, let's say a single API, or else it's only for the user space complete applications starting from the main?
Not sure what you mean. You mean by the user space? Can you?
Okay, so we have seen that the piece of code, it's a print K. Instead of that, maybe a kernel scheduler function, whether we can able to modify that on the runtime using this piece of code, or?
The philosophy of Zephyr on user space is not doing like this. Like in user space, you have to here you can create a thread. So you can create a thread as a user or the kernel thread. There is no limitation. It means the extension can create a kernel thread. So it could take control of your board. And if you want to create some objects, you have to give the permission here. So the extension cannot give itself the permission. So it's not working well now. About the user space. We have one question here.
I just had a question.
Sorry.
Just wondering about the security implications for this. Like, does it open up the possibility for injecting some bad code runtime? And what could be done to protect the applications? Or
I think. As I said, like if it depends. First, you have to make sure, since you are using the file system, first you make sure that no one can read your file system, because if you can read the file system or write into it, you can do anything you want. And then you have to make sure that your code is coming from a secure source, so you can use like a GPGK to say, okay, it's a package from Schneider. And then you use your private key and public key to say, okay, it's cipher, so it's not possible to modify it. But then after, I don't know if when you load the application, if you have to add some security, maybe just MD5 sum is enough, or maybe you have to cipher it as well. I don't know. So I would like to talk with the community about that to get their idea.
Questions for Cedric? All right, thank you.
Thank you. Sure. Yeah, check, 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 check.
Hello, I think we're live now. For those who don't know me, my name is Chris Freed. I am recently acquired by TensorTorrent, formerly of Meta. And yeah, this is my talk on the POSIX roadmap for LTS version 3. So just so in case you're not aware what LTS means, it's long-term support release. That's the version of Zephyr that's supported for at least 2.5 years. It overlaps with the previous LTS release by 6 months. And the LTS v3 release is scheduled for July 26th of this year. And one of my roles in the Zephyr community was LTS v2 maintainer. So what that means is that by this time next year, I will not be your LTS release manager. You will be in the very capable hands of Alberto Escolar, native POSIX and Arch maintainer. So I just wanted to say the last 2.5 years have been worth every second. So thanks very much, Zephyr community. And then I guess I'll be, yeah, here we are. So today we're going to talk about what role POSIX plays in Zephyr, a little bit about how it's organized, kind of the goals for LTS v3. This is almost like a refresher of a talk that I gave last year at EOSS because I wanted to follow up and make sure that I was on track and had all the community engagement and that sort of thing. So yeah, I'll just get into it because I think the topics are self-descriptive. So POSIX is a library that lives between the application kernel and subsystems. Ideally, it would be a very thin interface between those things. And I mean, portable operating system interface is kind of self-descriptive. And the last part of that is important because the interface is meant to be consistent, not the implementation. That's how POSIX applications achieve source level portability. Here's a brief overview of POSIX in Zephyr. I'm not going to go over the whole thing. It's just here for reference. I find it kind of fascinating to see how it's changed hands over time. In any case, it's been very much adding things on an as-needed basis, so almost in an ad hoc fashion. But yeah, it started out with sockets way back in the day, and then now we have dynamic thread stacks and everything. So I guess at the very end of that graph is where you'd probably see TensorTorrent now as maintaining the POSIX subsystem, or API, I should say. So one of the topics that we have to discuss, just because it's probably not as familiar to many people, is this concept of application environment profiles. So effectively, we have this nice Venn diagram that's fully concentric, which is great. So at the bottom, we have the base definitions. Actually, that should be updated to system interfaces. My mistake. I'll fix that on the slide. Above that, we have PSE 5.1. Above that is PSE 5.2, and then PSE 5.3. There's also a PSE 5.4, which is for effectively a multi-purpose real-time system, like a Linux desktop, for example. There has been a little bit of a change since the early days when this terminology was introduced. So originally they were called AEPs, which somehow gets translated to PSE. It could potentially be like a multilingual thing. I didn't find an actual definition for that acronym, but that was way back in 2003. So I think it could have been 2008 where they switched over to sub-profiling option groups. So that's instead of this application environment profile. And I guess with all the identifiers that I'm going to be listing in the coming slides, the way that you differentiate between an option group and an option is that the option has an underscore prefix. And this should be corrected. I don't know if you can see, no, you can't see my pointer. Where it says base definitions, it's actually system interface, sorry. So I guess starting off, the very basic fundamental requirements are these, basically like asynchronous I/O, which we actually do not support. I don't know if there are a lot of people out there that do support it. Barriers, clock selection, et cetera, et cetera.
I'm just going to try and breeze through this part. So if there are any questions at any point, feel free to just interrupt me. That's fine. But these are all the fundamental building blocks. We've got multi-threading, synchronization, real-time signals, memory mapping. Yeah, Keith. Yeah, that's going to be part of the documentation, and we have started labeling it. It's kind of subtle right now, but hopefully that gets clearer as the documentation matures. So an interesting tidbit is that real-time signals here are mandatory. I don't know what number it is, like, you know, the 8th down from the top, whereas like the generalized signals are not. So it's actually kind of interesting. So moving on, we have PSE 5.1, which is the minimal real-time system profile. It has some additional things, POSIX device I/O, like standard in, standard out, standard error, fopen, etc. We've got file locking, single process, XSI threads, which just kind of adds the ability to set and get your thread stack to a static array, a static memory address. And then signals, of course, which, as it turns out, is critical for high-resolution timers, which is another thing on the to-do list. And then, of course, as the list goes on and on, I'm going to skip again to the closer to the bottom. POSIX or POSIX shared memory objects are actually quite important, and we'll get to that a bit more later. But right now, without an MMU, like we do have an MMU API internally, but I think it might be best for us to assume that we don't for the purpose of conformance until we can actually tie that down. So we'll get to that in a bit. The last thing I wanted to mention is the POSIX thread sporadic server. It's an interesting way to introduce non-determinism into your execution of a multi-threaded system, which is good just to test the robustness. And then, of course, PSE 5.2. This is a real-time controller system. And what you'll notice is that these are just additive onto the previous system profiles. So the delta is actually much smaller than what our documentation page makes it seem. Of course, like this one just adds math support, file descriptor management, which is things like dupe, fgetpos, ftruncate, file system accessors, like change directory, remove directory, stat. Keith. I do not know the answer to that question. But I think that I know you've asked me that before. I think the thing is with POSIX, they always defer to the C library. So that's a good question. I think that's probably beyond, well, I can only do so much. I'll continue on. So mapped files, of course. And again, without an MMU, this has to be a physical address if you're mapping files. Yes? Oh, repeat the question. Sorry. Keith's question was, do we have any details on the POSIX extensions to the ISOC math library routines? And my answer is I don't know. And definitely, we haven't taken any significant measures to support like Bessel functions or anything. So if it's supported in picolibc, then I guess it would be supported. Another interesting one is actually message passing. So yeah, of course, like message queue send, message queue receive, MQ send, MQ receive, that sort of thing. And continuing on, we get to the dedicated real-time system. I hope this visualization helps. Does that help? Yeah, good, okay. So in PSE 5.3, again, it's a relatively small delta on top of PSE 5.2. So with this, we get to multi-process POSIX systems. Processes are not something that we support in Zephyr. I think for the most part, we proceed under the assumption that we are running in a single process, a single address space, although there's probably some minutia in terms of how that's interpreted and so on and so forth. So deviations from the POSIX specifications are, of course, documented, and we'll try to make every effort to document those.
Who knows though? Maybe in the future we will support some actual processes with separate address spaces. And then again, POSIX networking, which is awesome. Actually, Yuka just helped to finalize that, and of course, he started that whole effort to support POSIX networking in Zephyr. So, another thing, I think I skipped this on a previous slide. I'm going to jump ahead again. POSIX CPU time here refers to the amount of time that a process has, including all the children, all the threads that run in that process, how much CPU time it's actually taken up. There's a similar POSIX thread CPU time, which I think would be extremely critical for us to implement. That's a bit of the low-hanging fruit thing. So I'll try to summarize any missing pieces at the end, and hopefully we can, entice some new contributors and that sort of thing. And of course, sporadic server is very similar to the thread sporadic server, but at this level, it's the process sporadic server. Yeah, that's a little bit tricky. So, I mean, technically speaking, if we build Zephyr using the sporadic scheduler, then that would be supported. We don't have that yet, so it's a little bit outside of the scope of what we can accomplish with what we have. And that's why I have this little cross logo thing icon. So that is actually sort of consistent with the upstream Zephyr documentation. But again, we're going to try and improve the documentation so that there is a more structured way to represent deviations. So I guess a question that everybody always asks me is why POSIX? Why POSIX and Zephyr? It's a portable, mature API. You get portability, you get a confidence that your application will run from one target to the next, which is really useful. It's been incredibly useful for all network operations. There's a little bit of it sort of served as inspiration for a lot of our scheduler API and a lot of our file system API. And of course, this is very approximate, but approximately 2 billion POSIX devices in use as laptops, that's the little icon, desktops, and I have a filing cabinet there as a file server. So there are many POSIX systems out there. And of course, bigger than all of that is mobile. Mobile is everywhere. Everybody has a supercomputer in their pocket nowadays, all running a POSIX operating system. And even within that device, you could have like a POSIX RTOS, such as Zephyr or something like that, running on one of the real-time cores, which I find fascinating. And the last one I wanted to point out is, this is again a rough approximation, but there are a lot of incumbents in this field where you have a real-time POSIX certified RTOS that's controlling the infotainment system and perhaps some of the other aspects of an automobile. It's usually safety certified and all that stuff. I'll get to that a bit later, but automotive is actually a pretty key market. So our goals, this is actually a really quick section, recapping what I had stated last year. So we want all of the POSIX system interfaces. Those are what I called the base definitions earlier. It was mislabeled, my mistake. I'll fix that later. We want to support PSE 5.1, 5.2, and 5.3 so that we can give so we can give POSIX customers a good base to start off with, so they can move their applications and libraries in with ease. And then, of course, we wanted to improve maintainability, we wanted to improve conformance, and portability. And documentation is actually the last one, of course. So now we're on to how's it going? How it's going. So one of the things that came out almost immediately after EOSS last year was that the source tree needed to be restructured. We needed to make things a little bit more organized. Like how we typically do in Zephyr, where you have, I should have shown my screen here, but how you typically have like a kconfig.feature A, kconfig.feature B, and then you include those kconfigs from the main kconfig. It makes everything much more modular and scalable, I would say, because then you can keep all the details in a separate file. CMake doesn't have to kind of follow that rule to some extent. And then, of course, conformance options. So there are a couple of different facets to conformance. One is application conformance, which is when the application says, I want POSIX C source equal to the 2017 version of the specification. And that key will allow all of the various functions and structs and definitions to be provided in the C header file that you're including. And then, of course, there's application conformance, which is if your implementation implements, these, fread or fwrite, all these combinations of things, then you can say that you support this sub-profiling option. So that's kind of the emergence of that came out of the PSE sort of thing. So, and then of course, actually Keith is right here, which is good. One of the things that we're really striving to do is to ensure that we can incorporate as much stuff from external C libraries as possible when that external C library has an already mature suite of POSIX functions. So Keith and I will definitely follow up on that. Yeah, so since last year, the test suite has increased by about 1,000 lines of code. Some of that has actually been us shrinking other test suites within POSIX while simultaneously adding new lines of code. So the test suite is growing, which means that we're doing our homework, we're making sure that we're not breaking things, we're compiling against multiple libcs, so it's pretty good. One thing that really kind of irked me, and it's still an issue, and I'm hoping that Yang Kong, who's a collaborator, can help with this too. We need to go through the various POSIX kconfig options and make sure that they line up almost directly with the specification name. So for example, config POSIX networking, POSIX, sorry, I mix the pronunciation regularly. Config POSIX networking, which is a kconfig option, should translate directly to enabling the POSIX networking option group. And the same can be said for various options within POSIX. Portability, yeah, I think I already mentioned, and sorry, I copied this from the previous slide, but we're testing against the minimal libc, newlib, and pico libc. And I think actually in some cases, at least for a while, we were testing against the native libc, if only by accident. Documentation. I personally feel that it's improved. I think we still have a ways to go, but effectively we restructured the POSIX documentation and broke it down into smaller, manageable chunks instead of being a single monolithic page. So I personally find it better, but one thing that's missing, as I mentioned, is we actually don't have function level or struct level doxygen. So, and that's a huge endeavor actually. So I think one of the only feasible ways to do this is actually to either hire an army of new graduates, interns, or whatever, to do this for you, or basically write a parser to kind of automatically generate, or maybe just ask ChatGPT. I have no idea. So definitely, if anyone's interested in helping doxygenate some of the POSIX functions, that'd be great. And ideally, we wouldn't just copy stuff right out of the spec, because I think that's copyrighted. We'd have to use our own words and that sort of thing. Okay, this is where I guess it gets a little bit more interesting. So the system interfaces, which I incorrectly mislabeled base definitions earlier, for the most part, this is pretty good. Excuse me. So the only two critical ones that are missing right now are map files and memory protection, which is, it has a little bit of a nuance, especially on MMU-less systems. It is possible to do that, but for example, if you're mapping a file on a system that doesn't have an MMU, it's got to be a physical address. So you can make that happen, but it's going to take some additional checks. On a system with an MMU, of course, you'd have paged memory and that sort of thing. So you can just take an arbitrary address that the MMU gives you and apply that to whatever memory mapped file you have. And then, of course, you're going to intercept those I/O calls to that file when you're doing things with it. A lot of these things weren't implemented last year, so it's actually kind of great to see them implemented. And it's not just me, it's not just Yang Kong. We've had a lot of people come with kind of drive-by PRs, which is fantastic. And I encourage everybody to keep contributing because I think it's fantastic. Something that I'm doing myself right now is actually implementing signals. This might sound distasteful to some because signals, for the most part, introduce, especially if you're using signals to kill a thread, it introduces a lot of non-determinism into a system that is otherwise deterministic. So probably what we'll do is for those signals that would terminate a thread or a process, we might just ignore them unless you specifically say that you want that thread to be terminated. Because if you terminate the thread and it's got a bunch of resources associated with it, right now we don't have a way to free those resources automatically, like what's done in Linux, for example. Again, real-time signals, a major difference here between real-time signals and regular signals are that real-time signals have to be queued. They have to arrive in a determined order. They have to be handled in a determined order in order for the system to be deterministic. Really good opportunity if someone's new to Zephyr and they want to take a crack at some PRs. Thread safe functions, these are for the most part the _r variants of various things like read dir _r, because it gives you, of course, picolibc already has this. I can see Keith kind of like shaking his head. But yeah, so ideally we would have support for POSIX functions even when we're using a different C library. So that's kind of the methodology there. And then eventually we would harmonize. Along with signals, real-time signals, regular signals, etc. I'm handling pthread kill right now, which is sending a signal from one process to another. So that's kind of interesting, I'd have to say. So I'm excited to land that soon. We've had one drive-by contributor just start doing stuff for POSIX device I/O, which I find also fascinating. And I'm going to encourage them to keep doing that. So file locking, it sounds fairly trivial, but we'll see how that goes. I think that's another great first issue. And then the regular signals, which are handled with like a sig set and bit masking, that sort of thing. Yongkung did most of the work for that at some point. Oh, sorry, I'm just gonna get my water. Does anyone have any questions about any of the options or option groups so far? No? Okay. XSI threads extension, I think I already mentioned. It's just a way to set your thread stack. Of course, threads base. Currently only missing pthread kill, which I kind of consider almost done at this point. So. And of course, PSE 5.0.5.1 in terms of just the options. As I mentioned earlier, memlock, memrange, these are things that sort of assume that you have an MMU. If you don't have an MMU, it's very difficult to do this. And you might as well just say it's not supported, so E not sup, sort of thing. Thread CPU time, we have all of the plumbing in place in Zephyr to make that happen any day. Anytime anytime someone wants to implement that, I'll gladly review it. If not, I'll be getting to it shortly. The other things like priority inheritance, protection, that sort of thing, most of these were contributed fairly recently by, again, like drive-by PRs. People that have probably been active in Zephyr at some point in history, but haven't been back for a while. So it's really good to see people coming back and making those contributions. Again, in terms of PSE 5.2, it's just a very small delta for this feature set. And it's almost misleading when you look at the documentation on the Zephyr project site. I think that's something we need to fix because on the project site, we kind of repeat all of the options from the previous PSE level. And so it actually looks like it's more daunting than it actually is. So progress is going pretty well. In spite of, the size of the list, we're at about 80% completion for this already. FD management, which is another thing like, duplication of file descriptors and that sort of thing. Getting the offset, that's in progress. So we've had recently one developer come in and start submitting PRs. File system. We've actually had the file system support for a very long time, and maybe I would skip back, but maybe it's better to avoid it, but file system support was one of the first things introduced way back in 2018. So it's mostly implemented. There are some additional things that we do have to implement, and that's actually another place in our documentation which is missing right now. So I did ask a recent contributor to fill it in, so hopefully that gets added. So with PSE 5.2, POSIX shared memory objects are actually pretty important, especially moving on to the next level, PSE 5.3. Trace support, I'm actually not super crazy about implementing this. Zephyr already has trace points. They might not be perfect, but they're there. If we ever want to really optimize this, we can potentially do that. So I'm tempted just to say like e-not-sup for POSIX trace. It'll be linkable, that sort of thing. Excuse me. But when you try and run that code, it'll probably just give you a log message that says, please use the Zephyr POSIX tracing API. And now moving on to PSE 5.3, which is again just like a small delta over the previous revision. Multi-process, this is kind of out of our control at the moment. We're probably not going to support multiple processes for the foreseeable future. It probably won't be there for LTS v3, and it's certainly not going to be driven from the POSIX side. It's going to be a kernel thing. Pipes are like super easy. It's a unidirectional communication channel with a read end and a write end. So this is again like a great opportunity for our first PR. And then signal jump. Signal jump is, as much as it might sound intimidating, it's not that bad. You basically just mask your signals, or you save your signals, do your jump, and then you restore the signals coming out the other end. Pretty simple. Progress is going pretty well for this as well, in spite of what the documentation says on the Zephyr webpage. So I think that's something that we're probably going to have to correct sooner than later. One area that I think the network maintainers will have to jump in and add is raw socket support. So currently we have a number of different socket protocols, but as far as I'm aware, I don't believe we have raw sockets. That might have changed recently, because I know that Yuka added like a packet sniffer for the network subsystem. I don't know why the monotonic clock is here. Sorry, that's a typo. I'll fix that on the final copy. Monotonic clock, of course, like, I don't know if anybody watches Doctor Who, but are there any Time Lords in the audience? No, okay. We know that you're there. That's okay. So yeah, of course we need the monotonic clock for keeping track of stuff, but that's way back at PSE 5.1. So I think probably like if all of the cards are played right, I think we might actually be able to get all of these checkboxes checked for LTS v3 release. Probably with the exception that we won't support, at least not at the beginning, paging of anonymous memory and memory mapping with virtual memory. So that's a bit of a niche, and I think currently it's limited to x86 and 64-bit ARM. So we've improved maintainability a bit. Conformance is getting there, but it still has a little bit of improvements to be made. Let's see what else. Portability, we're testing against multiple libcs, so it's pretty good. It could be better. I think I'd like to pull in a lot of the things sort of from Pico libc, at least the style. So again, I'll be following up with Keith about that. Documentation is good. It could be better, but it's definitely an improvement. One aspect of this that I didn't mention yet, I sort of alluded to it earlier, was that automotive is actually going to be playing more of an increased role, I think. So there's a standard called AutoSAR, and specifically adaptive AutoSAR. I'll get into it in a minute, but within 24 hours of being at this conference, I was already approached by 2 companies involved in the automotive sector, and they were already asking for, when can we actually put Linux and Zephyr into a car and have it certifiable? That's a big question. I don't think we'll be there for LTS v3, but we'll probably be in a good place for our community members to get started. So as I mentioned, signals, that's something I'm working on right now. The next big thing, which would be kind of useful to unify all the file operations and that sort of thing, would be something I call ZVFS, my mistake. So that would be putting like F control or ioctl or read, write, that sort of thing, all on a central place where the various subsystems can leverage them all kind of in a more organized fashion, so that there are no layering violations and cyclic dependencies in the APIs. Because previously we had, for example, the network subsystem referencing POSIX, and the POSIX subsystem referencing the network subsystem. With this, we break that dependency chain, so there's a third item that both networking and POSIX can depend on. There are some similar dependency chains and threading, actually, but that's actually not a pressing issue. So, and lastly, doxygen. I think it would be great if we could get some function level doxygen done. And of course, so what next? What else is next? So, like last time, I think we're just going to create a bunch of GitHub issues, try and raise some awareness, and ask people to contribute code and make me review your code, and make Yongkang review your code. Anyone else who wants to get involved, please feel free. We have lots of spare time. I say that very, very sarcastically. It shrinks over time, but let's see. One of the issues, one of the topics that I wanted to bring up is, again, AutoSAR, adaptive AutoSAR. So it's built on POSIX. People want to certify their products with Zephyr and Linux, and I think that this is something that we might have to actually start taking more seriously. So the big question is, who's going to do this work? Who's going to pay for it? Because it's not super cheap. I guess it would be most likely auto manufacturers. But with that, we would join a relatively small number of real-time operating systems that are also certified POSIX compliant or conformant. In addition to that, we've got ARINC, which is, I forget what that actually stands for. It's aeronautics, something or other software systems. And one that I've been involved in personally is DSO 178C, which is safety critical aviation software stuff. Relatively new to me as well is this FACE consortium. I'd never heard of that, but it's actually part of opengroup.org, which is the same organization behind the POSIX spec. So this is a way for POSIX to get into aviation. I was doing it, I think, before there was a consortium for this. So for me to see this, I think it's quite amazing. Yeah. So of course, with automotive, with avionics, that sort of thing, we want to have automated systems doing things. And when we have automated systems, we think of AI nowadays, because everybody drives a Tesla and this and that. So everyone wants AI in all their systems. So And they're in everything nowadays: intelligent vehicles, hyperscaler infrastructure. In your mobile phone, people have these AI accelerators for inference and that sort of thing. If you're doing image detection or, even just human biological motion, like walking and stuff like that. In any case, I know of a great AI company. I've got some stickers if anyone's interested. And I don't want to give away too much, but the future is open source, so I'm looking forward to it. And with that, I'll open up to questions. Any additional questions anybody has? Okay, well, thanks for attending. And I hope we can all get to LTS v3 together. So.
Check 1, 2. Check.
Hello, everyone. I'm Ryan Erickson. Today I'll be talking to you about building products faster with Zephyr and MicroPython. I'm with Azurio. I've been with Azurio for 15 years now doing wireless products. And our company has actually been around for over 40 years developing products and wireless products now. I want to highlight our new company name. We were formerly Layered Connectivity. We're now Azurio. We do wireless modules, IoT products, and all that. So please check out our website. It explains why we changed our name. You can talk to me after, too. I can explain a little more. But all right, today we're going to go over what Canvas software suite is and how that plays into MicroPython, all our supported products, and then we'll get into the good stuff about how we made this happen. So first, what is Canvas Software Suite? Canvas Software Suite is our software platform for enabling rapid portable development across all our microcontroller-based products. First is the firmware, which is where the Zephyr and MicroPython come in. We have a set of tools that helps users work with that firmware on the product. Of course, there's samples, and then documentation like API documentation and all that good stuff. So first is the firmware. We have many platforms out there. I'm going to talk more about what those hardware platforms are in the near future here. A lot of my slides will have links, so you can get to all the reference material pretty easily. After the presentation, you can download the slides and all that. Along with the firmware, we have a set of tools. First, the most important and user-facing one, I would say, is our Visual Studio Code extension. This allows users to create, load, and interact with Python code on the device, as well as editing your Python code and running it. You get access to the Python REPL through the terminal interface in VS Code. So that's really nice because it's cross-platform. We also have a desktop application, and why that's important is we'll have certain firmware that runs on devices, and we want to be able to demo and show stuff off in a graphical way. So our desktop app allows us to write JavaScript-based applets very quickly to visually represent data as we need. And this also allows our customers to do the same. In the future, we'll be creating more documentation and make it more clear on how users can use that desktop app to build out and really quick proof of concepts. We also have a mobile app that effectively does the same thing as the desktop app, runs the same exact applets, just on a mobile platform. So that's really nice when you need something smaller. And also, it's nice for being able to do over-the-air updates to our devices. And then, of course, samples. We have all our Python samples out on GitHub, and we're continually adding to them and updating them. And last but not least, the main website, where it collects all our documentation and gives you the overview of the platform. When you have time, I highly recommend checking out the website here and watching our little overview video. So what products are supported from our portfolio? A lot of them. We are able to bring this up in a relatively short time because of Zephyr. All of our products contain BLE, but I'm going to touch on a couple of the more unique ones. Our newest product is our Sarah NX040 in the top left here. That's our BLE plus UWB module, which allows really accurate locationing. So that's really cool, and I'll be touching on some more of that throughout the presentation. And then also our Centrius MG100 gateway. So of course it's got BLE, but it also has cellular, so you can get your BLE data to the cloud. So some of the sample apps, I got them grouped here by platform to kind of highlight some of the main features. Of course, all of them, as I mentioned, have BLE. So any BLE you write in Python on one will work the exact same on any platform. So that's really handy. Our UWB module, we have a ranging demo that will talk to a tag, will talk to 3 endpoints, and with our desktop application, give you a 3D location visualization in a room. So that's a pretty cool demo. And then our gateway, we have our BLE to MQTT sample that people can customize for their needs. All right, now I'll get into the architecture here on how we built this and made this possible. So it all starts with MicroPython. For those of you who don't know, MicroPython is an implementation of Python 3.x that is designed to run on microcontrollers. MicroPython provides ports for different embedded systems, and a port could be based on an RTOS or it could be a bare metal based port. MicroPython provides the source for all the core subsystems that are used, for example, file systems, networking, USB, and many of these subsystems are based on other open source projects. So similar to Zephyr, they're pulling in these other pieces of source code to build upon. One of the problems as you look through some of these ports is many of the ports vary on how complete they are. They'll give you some features, but maybe not fully everything you want, and some of them are not well maintained. Another thing is when building a final product, firmware updates are very important. I'm going to mention that several times today, but I think we can all agree in this day and age, if you don't have firmware updates, you're not going to have a product. So that's why I'm going to stress it so much today. So we first took a look at the MicroPython NRF port. This port is quite outdated. Its BLE subsystem is based off the old NRF5 SDK, which is their soft device. So, Nordic has now moved on to NRF Connect SDK, which is based on Zephyr. So right away, when you look at something like this, it's like, it's not worth using, right? It's no longer supported by the vendor. You're going to have problems with Bluetooth qualifications. When you do an end product, these certifications and qualifications are needed in order to sell your product. So there's no RTOS benefits, and of course, you'd have to manually add all the features you want yourself, which is a lot of work. Next, MicroPython has a Zephyr port. This is getting close to what you would want, but there's a few things that aren't ideal. First of all, it's not up to date with the latest Zephyr. Now, sometimes being up to date doesn't mean everything, but it is nice to be able to be somewhat up to date so you can pull in new features as needed. It doesn't leverage all of Zephyr's subsystems. It uses its own virtual file system. The BLE features are not fully featured, and this is because of lack of, call it a Python glue layer for gluing the BLE APIs in Zephyr to the MicroPython subsystem. For example, there's no extended advertising or scanning. You can't use all the PHYs. And again, they're not taking advantage of the bootloader firmware update support that Zephyr can give us. Just going to touch on this quick. Can't talk about architecture without a stack diagram like this. So just to highlight, on bottom right here, at the lowest level, we got our vendor SDKs and libraries. In this case, Zephyr's kind of sitting there for us. And then at Azurio, we've developed some layers here, which we call our platform middleware. And that's allowing us to kind of abstract APIs from the scripting engine which lies above it. And the reason this is important is in case We do have a product that doesn't support Zephyr, which we unfortunately do with a couple of our modules because they're based on a silicon that's not fully supported in Zephyr yet. So that's where developing those extra layers benefits us, so we can still build MicroPython for them and have it work the same way. All right, so now we'll get into Canvas MicroPython, right? So the difference here compared to how I've seen everyone else do it is Zephyr is the core. So we build Zephyr first, and MicroPython has been added as a module. So because of this, we can benefit from all Zephyr's features. Their fully qualified Bluetooth stack, which is very important, networking, security, all that. And then we bolt MicroPython on with a thread. So first, here's a little snapshot of our manifest where we're adding MicroPython pieces, pulling them down. And here's a little quick snapshot where we're using sysinit to, on boot, start MicroPython up in a thread. So we were able to do this because MicroPython has what they call an embed port. The embed port is designed to embed MicroPython in any other existing C application. So we use this to our advantage because we were able to then turn that embed port into a Zephyr module. Also, in case you don't have Zephyr, it will work as well. So the first thing we got to get working on the device is a file system. It's one of the most important things with a MicroPython device. If you don't have a file system to store your Python files, you're not going to be able to do anything that's useful. So in Zephyr, with kconfig and device tree, you don't have to write any C code to get a file system running on your board. With kconfig, turn on the file system and pick what file system you want to use. In this case, we usually always use little fs. And then on the right-hand side here, you can see a snapshot of our device tree where we have a partition set up in an external QSpy, and then we use fstab to boot and auto-mount that partition. You can see the auto-mount flag right here. So it's linked to this file system partition, and on boot, it boots up and formats it if it's not already formatted, and you're on your way. You got your file system already running. Now the file system's running in Zephyr, we got to connect it to MicroPython though. So we had to implement a new module. We call it Zephyr MicroPython, and the purpose of this module is so we can glue Zephyr APIs into MicroPython. On the left-hand side here, you can see several of the different ones that we've done. Platform FS is for our file system, so that's what I'm kind of talking about right now. We've had to do some work with networking, time, and some UART stuff. So for the file system, the first thing we needed to do is implement the open function. This function is kind of special because it's the first thing that you need to do in order to get access to a file object, right? Everything in Python's an object. So this is the call into the Python framework, linking it to our open function, where then we call our Zephyr file open. Once you have your file opened, you need to be able to read and write to files. So MicroPython implements streaming functions, and they treat a file as a text file or a binary file. So this is showing the macros that are used in order to marry up the Zephyr API calls with the MicroPython system. So whenever you open a file, you have to implement your read, write, and I/O control streams, and that's, you can see here where we're linking into our specific Zephyr file read and file writes. And also, since we're using Zephyr, we get to use the Zephyr driver architecture, so that's pretty fantastic when you need to add some new hardware. We don't have to think about how to do it. We know how to do it because we've been developing with Zephyr a long time now, and just use the driver architecture. It'll standard way to do things. So we did this for our UWB module. We had to add support for the NXP SR040 UWB radio that's in our NX040 module. So here's a quick snapshot on the left-hand side showing the source tree for our new driver. We implemented some new DTS bindings, and then a couple C files for different layers of the API to talk to the radio. And then, because of device tree, we can easily add that new UWB radio in and attach it to the SPI interface here. And with those new DTS bindings, we defined our interrupt GPIO and the ready and reset GPIOs. So you do that, and now you have a standard way to access the SPI interface to the radio. Next, we need to be able to expose any C API we want to MicroPython. This is done with PYI files. So here's a quick snapshot of our UWB PYI. This is how we define a new API for MicroPython. We've got our init function, and then we can document what each of these does. And why that's nice is we have Python scripts to generate C stub code from the PYI file. That C stub code is used to do a lot of common code that's needed to integrate kind of the C in with Zephyr. And then also, that PYI file is used to generate our user-facing documentation. And then us at Azurio, we were the C developers that implement that C to Python API here. So here's a quick snapshot of getting a new UWB session. So this function right here is equivalent to the Python new UWB session. So when a user calls a new session from Python, this is the exact function that runs. It goes and calls any internal APIs we need. It uses the MicroPython APIs to create a new Python object as seen down here at the bottom, and then we return that object. So then in Python you have access to that object to then further use it in your Python code. On the right-hand side is a quick snapshot of our user-generated API from that PYI file. So users can come in and look how to use the APIs and see what's possible when they're writing their Python code. And here's a quick link to that. Connectivity is first for us. As we are primarily a wireless company, we need all kinds of wireless connectivity. So Zephyr has a fully qualified Bluetooth stack. It's certifiable. It's up to date. We get all the networking we need, any protocol we can ever want. We get security with Embed TLS. And as I mentioned, drivers, modem drivers, Ethernet drivers, and LoRa and LoRaWAN. And it all works and it's reliable, and that's what Zephyr gives us. Back to the firmware updates, right? You can't do anything unless you can update your product in the field. So Zephyr has a solution for that as well with MCU boot. The MCU boot bootloader is supported in Zephyr. Along with MCU boot bootloader, there's the MCU manager, which is your protocol for communicating and updating an image over USB or UART or BLE. And then also we are able to implement updates from the cloud, which I will get into detail shortly. So first, firmware updates over BLE. We use the SMP protocol that's built into Zephyr. SMP in this case stands for Simple Management Protocol, not Symmetric Multiprocessing. I know there's dual acronyms there, so it's confusing sometimes. With SMP, it gives you a standard way to do image management. Also, you can do file system management, which is great for updating your Python apps over BLE. And what's really cool is the SMP GAT service is always present no matter what the user's Python is doing. And we did that to make it easy, so the user doesn't need to know about SMP or how it works. Basically, if the user doesn't have a Python script on their board, by default, we have a default Python script that'll get up and run, start advertising, and make that SMP service available. So now you can connect to the device and firmware update if you wish. But if the user has their Python app written and they start up BLE and they're doing whatever they want with BLE, they want to advertise their own packets or their own, and then use their own GAT database to do whatever they want, that SMP service is still there in the background for use. And the user doesn't have to do anything. It's there to use, which is really nice. Firmware updates from the cloud are obviously very useful for managing devices when you have a bunch in the field. You can check out my last year's presentation. I went into a lot of detail about device management with Zephyr and Lightweight MDM. I got the link here. So I'm not going to go into super deep detail on Lightweight M2M, but we're using the Zephyr Lightweight M2M client. We use Object 5 for a firmware update. This allows us to update the core firmware, which in case we add new features to the core, that's important. Then we use Object 9, the software management object, to update modem firmware in the case of our MG100. And also this gives us access to be able to update the Python apps themselves, which that's what the user is going to be writing. We have a 0 configuration sample running in Python, so all you have to do, you go to the sample, you load it on our MG100 or Pinnacle 100 dev board. It boots and runs with literally no configuration, and it will automatically connect up to the public Lachon server, and you can test out firmware update in 5 minutes, up and running. So what's really nice is the user can control Lightweight MDM completely from Python. So we provided a Lightweight MDM API from Zephyr, so we made the common functions a user would want to access available in Python. So if a user doesn't want to use Lightweight MDM, they don't use it, and it doesn't start up by itself. They have complete control over starting it up. But what's great is the user doesn't need to know how the firmware update piece of that works. We've built that in under the hood, so when you connect and start Lightweight M2M, Object 5 and Object 9 are already there for you, already configured, and you can send a URL to each of those objects, have the device download firmware, and it knows how to flash it and do everything. So just to highlight, over here's a quick snippet of getting Lightweight M2M set up. You create a new object and give it an event callback, so anytime any relevant Lightweight M2M event happens, you'll get a print message. But then you have control over setting it up if you're going to connect with security with a pre-shared key or not, or use bootstrap mode or not. And then also Object 3 in Lightweight MDM is a required object, and that gives you information like manufacturer or firmware version and all that. So the user can set that up with these calls and set those fields in Object 3, wait for the network, and once you're on the network, just call Lightweight MDM start, and it gets up and runs. That's how simple it is. From that point, Object 5 and Object 9 are there, and now you can update from the cloud. Furthermore, besides updating the core firmware, users need to be able to update their Python apps. We've created a Python tool that allows you to package up your Python app. So your Python app could be one or more Python files. So you need to be able to package each of those files into some container. And we chose to use a zip container with no compression. And each file is also, when it's packaged, a SHA-256 is used, so when it's extracted on the device, we can know if the file's valid and there's not corruption. And then you get your packaged, versioned Python app, and with Object 9, you can download and install it. So just to touch on device management real quick. Again, Lightweight MDM is a really great protocol for device management. So we have that built into our gateway. Our partner Edge IQ offers a platform for managing your fleet of devices. Alternatively, there's the open source Eclipse Lachan project if you want to try it out and even use it to do your own servers. So with all this, reliability, of course, is top of our list. So we have an automated test platform. And why I bring this up is because with MicroPython, you get access to the REPL. So now with all our devices, there's a standard way to command and control them. So we've built a lot of tests with Robot Framework, and we've built functions like you can see here, user REPL send. And now we can send anything over the REPL in a standard way. We can automatically load scripts and run them and then look at results. So all our devices support BLE. We can run all the exact same robot tests on any platform, and we don't have to keep developing new tests because there's different ways to talk to boards. It's all the same. So this gives us a lot of confidence, and we can distribute new releases with confidence and do it very fast. So now I'm going to take a look at writing some Python. So I'll spend a little time on this just to show you. It's a little bit readable. I'll kind of touch on everything here. So this is a complete application for doing a BLE peripheral. I'll just highlight that it's only 60 lines of code, and that's all you need to get a BLE peripheral going with a custom GATT service. So on the left-hand side, we'll look from top to bottom, setting up a name and the UUID for your new service. We have a connection callback, a disconnect callback, a callback for writing to one of the GATT service UUIDs. A little helper function here for doing UUID to bytes. We set up our GATT table with a JSON structure. So for those of you who know how BLE works, you define a service. You have a UUID for that main service. You can name it whatever you want. And then you can have one or more characteristics in your service. And you can define them as read or writable or both. In this case, we're making this service writable. As we move down the file here, on the right-hand side here, we call BLE init. That gets us the BLE subsystem underneath all initialized. We set up our peripheral callbacks. We want a connection and disconnect callback. Those are our functions over here, so we can print out a message. We know we're connected or disconnected. And also on disconnect, we can automatically start advertisements again, so we're discoverable. And then we have a function to set up the advertiser, right? Peripheral advertises. So we get access to that new object, stop it, kind of clear everything out. And then we have some nice APIs for adding to an advertisement. Advertisements work by length tag values. So in the BLE spec, there are certain tags that are for different fields in an advertisement. So right now they're just defined as numbers here, so it's not too friendly, but you can look in the BLE spec for what 1 and 7 are. But this allows us to customize our advertisement very easy, and we can have control over what physical PHYs we want to use. In this case, we're setting it up to use the 1 and the 2 meg PHY, so extended advertising, and our interval, and then we start up our advertisement. And after advertisement started, we can start up our GATT server. And now the peripheral's running and advertising and ready to be discovered. So then the other side is your BLE Central. Again, only 60 lines of code to get your BLE Central going to connect to that peripheral. And I'll breeze through this a little faster. It's very similar. The only difference is we have a scanner and a scan callback where the discovered device will get printed. And we have a send message, so we can send something over to that peripheral. And again, a connection and disconnection callback. And so we init BLE, we call our scan init function and start scanning. When we get a scan callback for the device we're looking for, we log that here and connect to the device. In our connection callback, then we're doing we're getting a hold of a GAT client object, so that way we can send a message over to the peripheral. And then it disconnects. So that's a really simple, bare bones example of both sides of BLE. And then we take it one step further, getting that data to the cloud. So you would build all that same stuff. In this case, a lot of times a gateway may only need to scan. So for our gateway, we implement our scan callback. So when we discover that device, we can do some Python code for filtering, and that's what you're seeing here. So we can keep track of if we've seen the device, and we create a dictionary to store the device's ID. When's the last time we saw the device, its message, and then we can do cool stuff like rate limiting it. So here on line 79, if we've seen this device already, too soon, we just return out. Otherwise, if it's been long enough, we can pull out the data from the advertisement, update our dictionary for keeping track of that device, and then add that data to a list. And then we have a timer that fires, and we can pull data out of that published list and send it up over MQTT to the cloud. So again, this is way faster to develop something like this than writing in C, because there's no setup time, and you can, with the Python language, it's a lot more powerful. Looking to the future, we don't have everything done yet, but we do have a pretty complete system, but we're looking into implementing threading in MicroPython by hooking into Zephyr threads, so you would get true threading in Python. Adding in support for a little bit more flexible firmware updates. So right now, the only way to update from the cloud is using lightweight M2M. We want to add a Python API that allows the user to write an image to the firmware update slot and make it easy for the user. So what that would allow the user to do is download an image from the cloud in whatever format they want, and then use a Python API to flash those bytes. And they don't need to care about where it's going, it'll just work. Also, we want to get some encrypted file system stuff going. Making sure your secrets are secure is important for IoT devices. We don't have all of BLE secure connections working yet. That's soon to be there, being able to pair. And then our friends at Memfault, they have a great platform for crash analytics and device metrics. We want to build some features into the core firmware for that. So in summary, development on devices with MicroPython is much faster. There's virtually no setup time. You download our extension of VS Code, connect to the board, and you're up and running. You don't got to compile any firmware, download any host tools in order to compile the firmware. You're getting production level code without writing anything in C. And last but not least, putting all the firmware pieces together in C is hard, right? We know this. We've had this feedback from customers time after time. And so we've done all that hard work to put all the pieces together, and they don't need to worry about that anymore. And that's it. Any questions? I'll highlight that Azurio has we have a Discord channel on the Zephyr server, so I monitor that frequently, and you can get a hold of me there. We don't have a room host. He'll bring you a mic. Thank you.
Cool presentation, thank you. I played around with MicroPython and other controller, and it's, at least for prototyping, I really liked it. But I had always a feeling that performance in the end was like 30, 40, 50% less. So did you have any like benchmark, how much it was like impacting the system?
We don't yet. We haven't needed to do anything where speed is a concern. I will say that I don't see any concerns with speed. I could see maybe if you're trying to do some really intensive sensor applications, maybe that's where you're going to run into problems. So we haven't got there yet, but I will say low power works just because we get low power from Zephyr. And the execution time really doesn't seem to be that different, but yeah, we haven't fully benchmarked it yet. Good question.
Thanks, Ryan. Is there an escape hatch for Canvas users to implement or bridge the gap, the feature gap between Zephyr and what's exposed in MicroPython? Or do they just have to wait for Azurio to implement it?
So right now, we're actively taking feedback, and we would implement it. We haven't open sourced this yet. There's no reason we can't. We just haven't taken the time to. We want to make this easier for people. So typically, that would be a lot of work for someone, especially if they don't know Zephyr. So that's why we haven't.
Hi. A quick question around DFU. You mentioned that you guys are using MCU Manager and SMP. Mm-hmm. So what does it need to happen to get a package that runs CircuitPython, MicroPython, and DFU to devices running your platform? So right now, we're providing that core firmware image. It's not open source, so we will be rolling out new firmware updates, so we will provide the binary. The binary is already signed. So with our desktop tools and our mobile app tools, we already have a way to easily just put the binary on there, and it will flash it over BLE or over UART for the user. But it's using standard protocols like the MCU Manager CLI could be used manually. All right, anyone else?
When you say low power is working out of the box because of Zephyr, what sort of current draw are you getting with your SARA module, for example, as in the low power mode? Is it getting right down to the low power sleep?
Yeah, couple microamps. Now, UWB is very power hungry when you are in a session, but you have control over that from Python. If you're doing something, then you can shut down and tell the REPL to go to sleep, and yeah, there's no difference.
So you could use your SARA module to say periodically do a BLE TX packet every second, but then every now and again turn on the ultra wideband to do localization or something like that.
Yes.
If you were doing just that sort of once a second BLE transmit, but you can still achieve ultra low power.
Yes.
Yeah. Okay. Excellent. Okay, thanks.
All right. Anyone else? Thanks, everyone.